in my talk, they are not very related to each other. First is about reverse Monte Carlo, and the second is about neural networks, and they're quite different approaches how to analyze X-ray absorption data, but they have also, each of them has its own field of applications and its own advantages and of course disadvantages too. So, but in any case, what we are doing here is analysis of X-ray absorption data, and of course, I think at this point, after so many days of workshops, you should be more or less familiar with it. But again, the idea is how to analyze X-ray absorption spectra, namely dependencies of X-ray absorption coefficient on the energy of incident X-rays. And what we are interested here are these tiny oscillations in the X-ray absorption probability that follows immediately the absorption edge. And these oscillations are because of the interactions of excited photoelectron with neighboring atoms, and these interactions result in interference of outgo of the created photoelectron and the photoelectron scattered by the neighboring atoms, and this interference pattern is recorded as these small oscillations in absorption probability. And the signal which we are recording, this EXAFS signal or extended X-ray absorption fine structure, is actually related to the bond length distribution function, G of R function here highlighted with red text font color. And basically, the whole objective of EXAFS data analysis is to extract this G of R function from experimental measurements. And we, of course, can use different tools for that. We can use standard fitting using FEFID or Artemis programs. We can use reverse Monte Carlo, as will be done in this talk, or we can use also machine learning methods for this purpose. So basically, why this G of R function is interesting for us, basically it encodes very different relevant properties of the structure. For example, if you look at the positions, I will try to move here, at the positions of radial distribution of function peaks, then these positions correspond to average interatomic distances or average bond lengths. At the same time, the area under radial distribution function peaks correspond to the number of neighbors or the coordination numbers. And finally, the width of these peaks correspond to disorder. So the broader the peaks are, the more disordered is the structure. And of course, we can plot this G of R function for quite a long range of different R values. And using EXAFS method, we usually can probe only the very first few peaks of this G of R function, because EXAFS on X-ray absorption is essentially local methods. They don't really have sensitivity to very distant coordination shells. Nevertheless, there is like more than just very first nearest neighbor shell, and there are somewhat cases where access to these more distant coordination shells is also of interest for us. So how we do address this problem, how we extract G of R function from EXAFS analysis. So in conventional approaches using programs like FEFIT or Artemis, you make some assumption about what is the shape of G of R function. So typically you assume that G of R are more or less Gaussian-like functions, and then you can introduce the parameters of this Gaussian function as a fitting parameter. So you can, if you replace G of R with a Gaussian function, you can get rid of this integral, and you end up with this very well-known EXAFS equation in its most often used form. And then the parameters of your Gaussian function, the intensity, the position, and the width of this Gaussian function are just fitting parameters which you extract from your standard fitting program. And then the next step in that interpretation is that interpret these fitting variables in terms of three-dimensional structure model. This is how conventional EXAFS data analysis approaches works. And of course, there are several issues with this approach. So one issue to address here is that this works very nicely only if you look at the very first coordination shell, or maybe sometimes on the second coordination shell. But if you look at the Fourier transform of experimental EXAFS signals, there are often, especially for crystalline materials, we see also contributions of more distant neighbors, of more distant coordination shells present in your experimental spectrum. Of course, it's very tempting to extract some structural information from these peaks, but it's actually quite challenging. And the reason for that is, unlike for the very first few peaks in the Fourier transformed EXAFS signal, these distant peaks is the result not of a single bond or not a single atomic pair contribution, but it's a superposition of quite many different photoelectron scattering passes. And if you plot how many scattering passes you need to include into your analysis, if you get to access to this increasingly more distant peaks in your Fourier transform of EXAFS signal, you will see that you quickly run into a situation where you need to account for hundreds and even thousands of different photoelectron scattering paths. And of course, for each of these scattering paths, you need to introduce this, at least these three fitting parameters, so coordination number, interatomic distance, and the disorder factor. And you end up with a problem which has way too many fitting variables that you can determine using standard fitting procedure. So that's why there's conventional wisdom in conventional approaches when you want to address these peaks from distant coordination shells. You really need to think about which passes are important, which are not important, somehow sort the important ones from not important ones, and it's getting quickly very messy and hard to extract any information which will not be compromised by our own underlying assumptions. A second challenge which we need to address is that this assumption that the peaks of radial distribution function are Gaussian-like is actually maybe not accurate for many interesting cases. For example, for nanomaterials and other disordered materials, the shapes of these bond and distribution function peaks can be quite significantly distorted. You can see these non-Gaussian tails quite often, and as a result, the Fourier transform of EXAFS signal will look quite complicated. And if you want to account for these non-Gaussian effects explicitly in your EXAFS fitting formula, you again will need to include more and more fitting variables, and quite soon as this fitting problem again becomes untractable by the conventional approaches. And one solution to both these problems, so problem of distant coordination shells and problem also of these non-Gaussian shapes of radial distribution function, is to use simulation-based approaches. And the idea here is that instead of starting with experimental data and doing the fitting and then trying to figure out what is the three-dimensional structure model, we start with some candidate three-dimensional structure models for which we then can calculate corresponding theoretical signal, and we can compare it with experimental data. And based on this comparison, we decide which of these structure models makes sense, and then we can do some simple statistical analysis to extract statistical quantities of interest from this structure model. And there are different approaches which we can use for this method. And of course, here we'll talk about reverse Monte Carlo simulations. So in reverse Monte Carlo simulations, the idea here is that, again, we do fitting of experimental EXAFS data, but the variables are not or typical R, sigma, and N parameters as in normal EXAFS data fitting, but directly atomic coordinates. And we are trying to benefit from all possible geometrical constraints and relations which are existing in this three-dimensional model to get as unambiguous structure model as possible. And so the typical workflow for this process is illustrated here. So we start with some initial guess of our structure. We calculate for this initial structure a theoretical EXAFS spectrum. We compare it with experimental data, and then we decide whether this structure makes sense, and we can update it afterwards. And then for this updated structure, we again repeat calculations of EXAFS spectra, again compare it with experiment, see if this new structure makes more sense than the previous one, and we proceed through this loop, through these iterations, until we find such structure model that fits well our experimental data. This is kind of the basic idea. And of course, when the final structure is obtained, we can calculate what are the actual average interatomic distances, what are the neighbors, and so on. So one of the first problems is how to choose this initial structure model. And the initial structure model for crystalline materials can be chosen quite simply. If you quite often you know X-ray diffraction data for the system, so basically you already know what is the symmetry, what is the lattice constants for this structure, and so it's already a very good guess of how the structure of your material might look like. So from this information, it's actually quite easy to obtain EXAFS spectra using reverse Monte Carlo simulations, since the point here is that reverse Monte Carlo simulations will just introduce some thermal disorder in this model so that the amplitudes of atomic motion matches those in experimental system. But at the same time, this approach can be applied, of course, not only for crystalline materials, but also for more complex cases, for disordered materials, for nanomaterials also. But in this case, we need to be more careful how to choose this initial structure model. And for nanomaterials, for example, good starting point sometimes can be structures from DFT simulations, from molecular dynamics simulations, from machine learning methods, as I will show in the next part of the talk, and so on. But in principle, in all these cases, the first step is to find out what is the initial structure model that makes sense for this material. So once this structure model is chosen, we can then calculate EXAFS spectra. For this, we again can use popular codes like FEF. And the difference between reverse Monte Carlo based approach and the conventional EXAFS data fitting here is that we are not shy of including more and more scattering passes here, because having more scattering passes in reverse Monte Carlo do not increase the complexity of the problem, because the number of fitting variables, so number of atomic coordinates, does not, of course, increase. And it is a very different situation from the conventional EXAFS data fitting, where every scattering pass which you include in the analysis makes your problem more complicated by adding more and more fitting variables. And of course, importantly, when we do this calculation of EXAFS spectra, it's important to remember that we need to average for signal over all non-equivalent atoms in our model. Well, because that's what we measure experimentally. We are measuring signal not from a single atomic site, but from all atoms of absorbing type present in our sample. And then, of course, the next step again is to compare experimental data and simulations. Different approaches can be used. You can use Fourier transform for this purpose, compare the spectra in a frequency space. You can compare them directly in K-space. In the code that I will be presenting in the next part of this talk, we're using Euler transform for this purpose. So I'm not going too much into details of Euler transform, but again, it's just a way how to extract information about what kind of frequencies are present in your spectra and in which parts of your signal these frequencies are most important. And then the update of the structure model, so basically the last step of this loop, can be done just by displacing atoms randomly from their previous positions. We can either displace all atoms by small amount or choose one atom and displace it by more larger distance. And in some cases, we can also apply more sophisticated structure updating schemes like swap to atoms, and this could be more relevant for studies of disordered materials or amorphous materials that we don't really know in advance where each atom is located. This kind of the basic steps which we need to do at every iteration of reverse Monte Carlo simulations. And of course, all the magic of reverse Monte Carlo is hidden in how exactly do we find this final structure which makes sense and gives agreement with experimental data. And the problem here is that the problem which we are trying to solve is actually quite complex one. So we have many hundreds of variables, atomic coordinates, and the function which we are trying to minimize, so disagreement between experimental EXAFS and theoretically simulated EXAFS spectrum, is a strongly nonlinear function of all these hundreds and hundreds of variables. So it has many local minima, and what we're interested here, of course, is not to find this local minima, but to find this one global minimum, the point which gives us the best possible agreement between experiment and simulations. And to do that, you really need to think about what exactly are your optimization schemes that you're using and how exactly it works. And in reverse Monte Carlo simulations, this idea how to minimize or how to explore this configuration space efficiently is basically borrowed from the conventional or metropolis Monte Carlo method. So just to introduce how direct or metropolis Monte Carlo method works, I will say that it's just a method how to sample atomic structures according to some desired distribution. So typical question that could be addressed by Monte Carlo method is you want to generate 1,000 atomic configurations whose energies follow, for example, Gibbs canonical distribution. And how can we generate these 1,000 configurations? So for algorithm proposed by Metropolis in 1950s. The idea was actually quite elegant, quite simple. So again, we start with some initial structure model, and then we modify atomic coordinates. We can recalculate, of course, the energy for this updated situation. And then we need to decide whether we accept this proposed atomic configuration or we reject it and return to the previous step. And this rejection or acceptance is based on so-called Metropolis criterion or Metropolis algorithm. And the idea is to compare the new energy with the energy of the previous configuration. And if the new energy is smaller than the previous one, so the new configuration is more favorable than the previous one, we of course accept this configuration. But the trick is that even if this new configuration has larger energy, we still can accept it with some probability, which is getting exponentially smaller when we increase the difference between this new energy and the old energy. And basically the idea here is that if you repeat this process for many thousands of iterations, we will sample these atomic configurations accordingly to this Gibbs distribution in this case. And basically the only difference between this conventional Monte Carlo method and the reverse Monte Carlo method is that instead of it is meaning of this parameter epsilon. So it's not energy anymore, but the difference between our experimental data and the theoretically simulated data. So again, to explain why it will work. So in the conventional Monte Carlo method, the structures which we will be generating, so we will be following this canonical distribution, which means that there is large probability to find system in a state where this energy, in case of normal Monte Carlo, is low. And if you use it for reverse Monte Carlo application, it means that there is a large probability for system to be in a state which has a low difference between experimental and theoretical EXAFS spectrum. So this is a basic idea. So by accepting some of the configurations which makes our agreement worse, we are ensuring that we are not stuck in the local minima, that we can explore this configurational space efficiently and eventually end up in a globally optimal point. So the structure which really gives us the best possible agreement between experiment and simulations. Of course, there is some additional technicalities which need to be careful with. For example, this scaling parameter T, which is in the normal Monte Carlo method, is just a temperature. Here in the reverse Monte Carlo, it's really just a scaling parameter. And you need to figure out what value it should have, because if you choose it to be too low, you will end up again stuck in some local minima because system will never be able to escape it. Or if you choose it to be too high, then you will just be randomly sampling all possible configurations and there will be no useful information coming out of this simulation. But at the end, the strategy which is again implemented in this code, which I'll be presenting in the second part, is the idea that we are having here is that this scaling parameter is decreased during the simulation. So we start with large value, and we have like significant, strong fluctuations in the agreement between experiment and simulations. And at the end of the simulations, we reduce this value of scaling parameter, and then we have a system where each of the consequent atomic configurations is more and more similar to the previous one. And we end up at final some state which gives us, hopefully, the best possible agreement in experiment simulations. This approach is called simulated annealing, and it's a quite efficient way how to do this optimization of your material structure. And importantly, of course, also is ensures that all the constraints which you may have or may be useful for this material structure determination are implemented. And one of the advantages of this reverse Monte Carlo scheme is that it's very easy to implement such constraints because if system ends up in some state which is unacceptable from your point of view for some reasons, then you can just apply some additional penalty for this disagreement between experiment and theory function to make these points which violate the constraints really unfavorable, and the system will always try to avoid them. So it's quite a simple way how to implement all these constraints, and this is one of the great strengths of reverse Monte Carlo method. And of course, you can have more sophisticated optimization algorithms implemented. So one of them is also implemented in this EVAX code, which I'll be talking about in the next part. So in an evolutionary algorithm approach, the idea is that instead of just one configuration, you're optimizing several atomic configurations in parallel, and you allow some information exchange between them with the idea, again, to improve this convergence and find this globally optimal solution faster. So just to illustrate why would you care about such an approach, what kind of research questions can be answered by reverse Monte Carlo simulations, what cannot be answered by the normal EXAFS data fitting. So again, the objective here is to extract not just atomic coordinates, but some statistically meaningful descriptors of your atomic structure, such as a radial distribution function or average interatomic distances. So for that, you will need to do some post-processing of your atomic coordinates. So of course, when you want to publish your results, you don't really report XYZ coordinates for all the atoms in your model, but you calculate, for example, a bond length histogram and or radial distribution function, and you try to analyze and report that one. And here you can easily get access both to the contributions of near neighbors as well as contributions of more distant coordination shells. Because you can also extract more sophisticated information. You can look into average bonding angles, see how the bonding angles changes, and all this more three-dimensional information can be extracted only from reverse Monte Carlo simulations. But even if we just limit ourselves to these pairwise interactions, only to this radial distribution functions, there is plenty of interesting information which can be extracted only from reverse Monte Carlo simulations. And here I will present some of the examples where it was really the case. So first example is actually original example, which was addressed using this program, EVAX code, and it deals with structure determination of rhenium trioxide. So this material has a relatively simple perovskite-like structure, so it's cubic material with cubic symmetry. Consists of just rhenium and oxygen atoms. And the question we tried to understand here was what's going on with this material when we intercalate it with hydrogen atoms. In this case, we form so-called hydrogen bronze. And if you look at this material by means of neutron or X-ray diffraction, we can determine the structure of this material, and we see that it's not so different from the structure of this original rhenium trioxide. Basically, we have small tilting of these structural units, rhenium O6 octahedra, but no really significant changes. At the same time, if you look at this material with EXAFS, with X-ray absorption methods, you actually see that the difference between EXAFS spectra for pure rhenium trioxide and for rhenium trioxide intercalated with hydrogen ions is actually quite significant. So EXAFS spectra change quite significantly. And this question is why? So why such a big difference between this relatively small changes in X-ray diffraction data and such huge changes in the EXAFS spectra? And we believe that this can something to do with correlation effects in EXAFS spectra. So if you look at these sigma square factors or mean square radial displacement factors, which can be extracted from EXAFS data analysis, it's important to remember that they depend not only on the amplitude of atomic motion, but on the relative atomic motion. So they also contain contribution of the correlation. And it's possible that you're in a situation where atoms thermally move a lot, but if their motion is completely correlated, the sigma square factors in your EXAFS data analysis actually will be quite low. And in the cubic materials, such as rhenium trioxide, the interesting feature is that these sigma square factors for atoms which are located within the same linear chain of atoms, they have very strong contribution of this correlation effects. While if you look at two atoms which are located in not in the same chain of atoms, but let's say at similar distance, but one is without this direct bond between them, then their sigma square factors will not have this strong contribution of correlation effects. And we can see this effect clearly if you plot how the sigma square factors extracted from reverse Monte Carlo simulations changes with interatomic distances. So these red dots, red circles here shows the MSRD factors for atoms which are within a chain of rhenium, oxygen, rhenium atoms. And these black circles show the sigma square factors for the atom pairs which are not within the same chain of this linear chain of atoms. And they're quite significantly. And you also see that the atoms, these red circles have some significant trend with increase of interatomic distances. So the correlation effects gets smaller when we look at more and more distant atoms, and this is not so clear trend for the sigma square factors for pairs of atoms which are not within the same chain of atoms. So the bottom line here, or the main point here, is that if you can look not only at the very nearest neighbors, but if you can have access to this radial distribution function peaks beyond the very first one, you can try to single out what is the contribution of the correlation effects in your disorder factors and what is the correlation of contribution of atomic thermal motion. And it seems to be the key what's happening with this rhenium trioxide upon hydrogen intercalation, because the quantities which are such as sigma square factors for the very nearest neighbors, they seem to be affected very strongly by this intercalation of hydrogen. And it indicates, and this has this strong influence on the changes in our EXAFS spectra, while the quantities such as bond lengths and their distributions for atoms which are not the very nearest neighbors or are not within the same chain of rhenium oxygen atoms, they are less affected by the presence of hydrogen, and they reflect basically just this small tilting of structural units, which we see also in X-ray diffraction and neutron diffraction data. So again, to maybe not important all these technical details, but the point is that only by having access to the contributions of these distant neighbors, we can sort out correlation effects from the thermal motion of atomic atoms. And then, of course, natural question is how far we can probe using reverse Monte Carlo simulations if we have perfect sample and perfect material. So far, I think the record in terms of how far we can probe using reverse Monte Carlo analysis was this study of metallic tungsten, but again, you can see these nice contributions of distant coordination shells present well beyond this main peak in Fourier transformed EXAFS signal. And in principle, all these peaks can be analyzed using reverse Monte Carlo simulations. In this particular study, in this paper, structure of metallic tungsten, which is admittedly quite simple material, but still was actually interpreted up to 10 angstroms, which is way far exceeds what you can do with conventional EXAFS data analysis approaches, even for such simple materials. So another important reason why to use reverse Monte Carlo is this question of non-Gaussian effect. And again, the idea here is that if you look at nanomaterials and small nanoparticles, for example, often these radial distribution functions will have these non-Gaussian tails, which will affect the final answers. For example, if you want to know what is the actual average interatomic distance or what is the actual number of nearest neighbors. So you need to account for these tails if you want to answer these questions. And the question is if we use these conventional approaches, so how big mistake can we make if we don't account for these non-Gaussian effects? And actually, it seems that in some cases, this error can be quite significant. And here, as example, I show the results obtained by conventional EXAFS data fitting and by reverse Monte Carlo method for such simple material as metallic zinc. So spectra was collected just for metallic zinc foil. And you can see that zinc, which has a distorted HCP structure, so two slightly different bond lengths in the first coordination shell, is actually a very challenging case to analyze using conventional methods. So if you do the fitting of EXAFS spectra with conventional approaches using FEFIT, you will get a quite reasonable fit, and you will never suspect that there is something wrong with the structure model. But the coordination numbers that you will be getting actually are just 50% of the actual true number of nearest neighbors. And this is because this Gaussian approximation misses completely this big non-Gaussian tail of your bond length distribution, which can be modeled and determined accurately by reverse Monte Carlo simulations. So clearly, in this case, it is really important to have this access to methods which can deal with non-Gaussian shapes of bond length distribution functions, because the answers provided by the conventional methods are just completely misleading and completely wrong. So in terms of reverse Monte Carlo simulations, again, for this study of gold nanoparticles, we were able to determine all these quite complex shapes of bond length distribution functions. And interestingly enough, actually, they seem to be quite independent on what exactly is the initial guess of the structure model, which of course is an important limitation for reverse Monte Carlo methods when they applied for studies of nanomaterials, because in principle, we need to guess in advance some kind of initial structure model. But it seems that the final Redel distribution function does not really depend so much on what initial guess you make. And of course, we can also address more complex models, not just metallic systems, or not just monometallic nanoparticles. And here, for example, is a spectra for cobalt tungstate nanoparticles. So again, these are small nanoparticles, which size are about 1 nanometer, and their EXAFS spectra can be collected both at cobalt K edge and on tungsten edge. And in both cases, we see they're significantly different from the spectra of corresponding bulk material. And this difference can be again interpreted using reverse Monte Carlo simulations. Important here for if you study more and more complex materials is that you want to introduce as much information as possible in your reverse Monte Carlo modeling. And in this particular case, it's always important to, if you have data measured at both absorption edges and cobalt or and tungsten absorption edges in this case, then it's important to include both of them in the reverse Monte Carlo fitting, because if you don't do that, you can miss important information about the local environment of another element. So just to illustrate this point, so here we did reverse Monte Carlo analysis for these copper tungstate nanoparticles, actually bulk material in this case. And we obtained a structure model from this reverse Monte Carlo analysis, and using only tungsten L3H data, and then we use this final atomic coordinates to calculate the corresponding theoretical EXAFS spectrum for copper. And it was completely different from the experimental measured one. And of course, so this kind of study, which again emphasizes importance to include as much experimental information as you have in your final model. Because of course, when we include both tungsten and copper edges in the EXAFS data fitting, we can find the such structure model, which gives us good fits for both absorption edges. And again, for studies of nanomaterials, it's important to remember that we need to figure out what is the initial structure model. And if you have several hypotheses, you can try several of them. So here we have the 4 different structure models indicated by A, B, C, and D here. And we wanted to find out which of these 4 models would fit our experimental data in the best possible way. And there are, of course, no absolute answers. And in this case, we were able to find out that models B, C, and D actually all give quite good agreement with experimental data. But we can clearly rule out this model A, because this model was the one that could not describe at all these contributions of more distant coordination shells. So this again emphasizes the importance of having access to these distant coordination shells, because especially when you're dealing with oxides, first coordination shell can be quite non-informative, because it just reflects that there are 6 oxygens around your absorbing metallic atom. And again, all these BCD models are quite similar, both in terms of final agreement between experiment and simulations. But if you really look at in details, you can find that maybe model B is a little bit fits data a little bit better than other models. But again, this may be not really a significant difference in this particular case. All right, so with that, I would like maybe to sum up this theoretical introduction to this reverse Monte Carlo method. And basically, the thing that we need to remember here is that reverse Monte Carlo method is just a simulation-based procedure, which allows you to analyze EXAFS data, experimental EXAFS data, in a way that allows you to account for contributions of distant coordination shells and for multiple scattering effects and for non-Gaussian shapes of bond length distribution function. And at the end, you immediately get the 3-dimensional structure model of your material with all these disorder patterns and complex effects accounted for. Advantages that you can use this three-dimensional structure model immediately as input for further analysis using, for example, DFT simulations or molecular dynamics modeling. Advantages also that you can easily incorporate constraints and also information from other experimental techniques just by making more and more complicated penalty function for different structures in your simulations. And of course, the point to remember here is that in reverse Monte Carlo analysis, the final structure is always only as good as your experimental data. And if you don't have some information contributing to your experimental EXAFS signal, you will not be able to extract it from reverse Monte Carlo simulations. Maybe just to finalize it, some kind of guidance in which cases these reverse Monte Carlo methods would work when they not. So in principle, if shortly, then you should use reverse Monte Carlo simulations if you know in advance what are your coordination numbers. For example, if you analyze crystalline materials, you know already what is the structure, so you know what is the expected number of nearest neighbors in different coordination shells. And in this case, the reverse Monte Carlo simulations can be quite powerful way how to treat your EXAFS data. And actually, it's much simpler to do in this case reverse Monte Carlo analysis rather than deal with all these different passes in Artemis or other conventional tools for EXAFS data analysis. And of course, you can also apply it for more complex scenarios when you study nanomaterials or amorphous materials, but then you need to be careful what is the initial structure model, and most likely we'll need to try different structure models before you find the one that gives you satisfactory agreement between experimental simulations. Very importantly, reverse Monte Carlo will not work very well when your material is a mixture of different phases, or material which experience phase transitions during your experiment. And in this particular case, as this machine learning methods, which I will discuss in the second part of my talk, will be much more beneficial. And of course, again, the point is that you need to have a relatively high quality EXAFS spectra, which should be relatively long, because if you don't do that, you can also again introduce some artifacts in your model. All right, so if you want to have some more information about reverse Monte Carlo, there are some useful links and useful papers which you can look at. And yeah, this site, Dragon LV EVAX, is a website for this code which we have developed for this reverse Monte Carlo simulations, and I will introduce it yeah, basically in the next part of my talk. So I imagine do we have some kind of time for questions now, because it will be a good time maybe to ask one or two questions, or
well, don't see any questions right away, but if something shows up, I'll read it, but I don't see anything right now. Maybe we'll have more questions when you start the demo.
All right. Okay, so the next item on our agenda was to introduce this code for which we can be using for reverse Monte Carlo simulations. And I think in you have already access to this folder, which contains the code itself and all the auxiliary codes and examples and files which are needed to successfully run this demonstration. Maybe I just want to point out again that a good starting point for all this introducing yourself with reverse Monte Carlo methods is this website, Dragon LV EVAX, where you can download both the code for free and use it for your application. But there is also recently added a library of existing applications. So basically, you can choose, there are some results of reverse Monte Carlo simulations for some common materials, which we discussed in this presentation, but also for many more. For example, you can go to nickel oxide, and then you can look how the reverse Monte Carlo result looks like in terms of fitting of EXAFS spectra. You can get access to the contributions of more different important scattering passes, what is the structure, how the radial distribution function looks like, and you of course can download all the input files and output files and use it for your research. All right, saying that, maybe I will now spend some time to demonstrating how to run these reverse Monte Carlo simulations, and maybe then we can have also some more time for additional questions if they appear after that. All right, so the current version of EVAX code is EVAX 5.1. So it's a command line program, which means you can run it. You need to open your command line interface. I hope you can see what I'm doing now, supposedly. And so you need to go to the place where your program is located. And yeah, here it is. You can find. So now I'm in the folder where this EVAX code is located, and just if you want to run it, you can just type the name of the command, EVAX exe, and basically click it, and it will complain in this case that it's not really have anything to work with because no inputs were specified. So you need to provide a file with parameters for the simulations. You can use some of the parameter files from the example directories above, but you can also use additional command example, which is a convenient way how to generate example file of with all the parameters needed for reverse Monte Carlo simulation. So if you execute this command, you can see that the new file appeared here in this directory, example.dat, and it contains all the parameters which you may need or don't need for the simulations. So there are quite a few of them, but the important point is that you don't really need to know all of them. You only need to specify those which are different from the default values, and the default values are given currently in this example file. All right, so an alternative way, if you don't like this command line interface, maybe more convenient way how to run it, you can just make some short script file, like a one text file with a sentence of the name of the program and the additional arguments you want to provide. And then you can just click that one and it will do exactly the same thing again, create this example file. So, and of course, all these commands which I'm discussing right now, they're described with these README files, which you can also read later for yourself. All right, to see how it works, the first example which we will cover will be a reverse Monte Carlo analysis for crystalline germanium. We can go in that directory, and basically we will do two steps. We will just plot the spectra for germanium, and then we will do reverse Monte Carlo simulation for this. So in this directory 001, we can find example which is needed to plot spectra for crystalline germanium and do some simple Fourier transform and wavelet analysis for this material. Again, we can look at this run file, just contains in this case basically the same command as previously. So in this case, the difference is that now we specified the name of the files with parameters, and we added second argument which tells us that we don't want to run reverse Monte Carlo simulations here, but just do Fourier transform and wavelet transform simulation. And of course, it's always a good idea to add this final part to your command line, so that the output is saved, not just printed to the screen, but actually saved to this germanium log file. And these additional comments are here, just added scripts for GNU plot, which I'm using here for visualization. But I will go back to that in a minute. So if you run this file, it takes a couple of seconds, hopefully. And yeah, so it plots your EXAFS spectrum for crystalline germanium. So it's a very nice quality data because this experiment was carried out at low temperature, at 20 kelvins, I think. And then we can look at the Fourier transform, which again contains strong contribution of nearest neighbors, but also many contributions of more distant neighbors. So there is plenty of information in the experimental spectra that you want to analyze. And yes, we can also look at this wavelet transform, which again, I will not be discussing too much here, but again, it's basically tells you that there is some strong contribution at 2 angstroms from a backscattering atom, and then some additional coordination shells at larger interatomic distances. All right, so this is kind of example, just demonstrates how to plot things, and we didn't really do any reverse Monte Carlo simulations. So to do this RMC analysis, we now can go to this another directory, this calculation. And I will first start the simulations, and then I will discuss what exactly is happening here, because it will take about 15 minutes for this example to run. So we'll have about 15 minutes for discussion. So here we can again create this script file to run it. I will create it now from scratch, basically. But they all described in this README example files also. So I will create small text file where I will just write the name of the program. I need to specify the file with input parameters. In this case, input parameters are hidden inside this directory input files. And this start Germanium file is the file with all the parameters, which we'll be discussing in 1 minute. So I need to specify this name of the file. Copy something like mistake. Okay. It'd be great if I could see my text editor here. Okay. Next time. And that's it. Yeah, we don't really need to specify anything else because we just actually I will specify one more command just to make it a bit quicker. I will skip some accuracy checks in the simulation, but this is kind of optional plugin. We don't really necessarily have it here. And again, I specify the name of this log file where I will save all the output from the screen. All right, this should work. I will save it. And I will go back to this main directory for this run file, which we just created. You can click it, and then, yeah, you can see that it started working because there is like a bunch of files appearing. And the J log file is this log file which contains all the output from the simulations. So we can look into it and see what's going on here and what are the information which we are getting at this point. So first of all the input parameters are again printed here to this output file, which is convenient because again you can see what exactly parameters were we using. And then you will see some additional output appearing as the simulations progress. I told you that it will take about 15 minutes for them to be complete, to finish in this particular case. So we'll have some 15 minutes of discussion of what's going on. And basically, how do this fitting? If you have done any EXAFS fitting so far with any other tool, you should probably be able to follow what's going on here, because again, these are the same building blocks as in your Artemis or in any other fitting programs that you may use. So you need to specify your structure model. So in initial guess of your structure, then you need to define how you want to optimize the structure model for how many iterations and so on. You also need to define what exactly are you fitting, where is your experimental data located, how this input spectrum looks like, how many columns it has, and so on. And then, of course, you need to define some parameters for path calculations, which will describe how many scattering passes you want to include, and how long is the distance you're interested in R space for included in the simulations. And then the final or almost final part is to define the ranges in K space and R space, which you are using for comparison between experimental simulations. So basically, all of this should be very similar to anybody who did any fitting of EXAFS spectra using any of the code. Then this, of course, the final part, it describes the names of the output files, and of course, maybe it can be more or less arbitrary. So I will start probably with discussing how we are getting the structure. So it's this here line specifies that the structure will be read from this P1 file. So it's another text file located in this input directory. And again, it's nothing sophisticated, just input file which describes a lattice constants of your material and the equilibrium positions of your atoms inside this unit cell. So you can create this file manually just by writing it by hand. You can open some old diffraction paper from 1920s or 1930s where the X-ray diffraction from germanium was published, and you can find all this information there. Or conveniently, you can use some special software for this purpose to create this P1 file. So I like to use Vesta software, which is a very convenient tool. So you can basically use it to define new structure with the parameters you're interested in, or even better, you can also use it to import the structure from a CIF file if you have it. Let me find it. So in this particular case for germanium, we can find easily in the internet many different CIF files with germanium structure. You can open one of them. You can make sure that this is the structure you're interested in. So this more or less thin blend type of structure, crystalline germanium. And then you can just export it as this P1 file, which we are talking about right now, which is currently used by reverse Monte Carlo simulation. So this structure definition is not too different from what we do in Artemis. Again, you start with some CIF files. You just need to export it in this P1 form, which is available within this RESTA program. All right, so this can be covers this question of structure definition. And then we can look again what else is going on with our input file. So with our input for simulation. So another part we need to specify was a experimental data file. So some of these parameters are more or less self-explanatory. So it just tells us that there are two columns in our file which contains our experimental data, and we already plotted this file before, so we know what's inside. But what's important here is that we also need to specify these SO2 factors and X0 corrections, which are the same factors which are important also for conventional EXAFS fitting. But here they need to be specified and in advance. So question how we can get these numbers, and in principle actually EVAX, this program does some effort in estimating them, which maybe give you some good guess. So if you look at this output file created by EVAX, somewhere at the beginning of the calculation, it reports what could be SO2 factor and delta E0 factor for this simulation, and also provides some information about the possible average interatomic distance, and all this is done based on this standard EXAFS fitting on the first coordination shell. Since EVAX is not really designed to be replacement of Artemis or Demeter or Pepit, it's doing quite simple fitting only, but in some simple systems like germanium, these numbers actually are quite meaningful, and you can actually see that in this particular case, they agree with the numbers which we used to start this simulation. So everything seemed to be fine with SO2 and delta E0 factor. So the important difference here is that this factor, delta E0, is different from the one below by minus sign, but it's because the question is what we are shifting, whether we're shifting experiment versus to simulations, or we're shifting simulated spectra to match experimental one. So it's some technicality, but we need to be careful with. In more complicated cases, if you don't know if this simple fitting of the first coordination shell by EVAX is not really satisfying you, you can try to, of course, use a SO2 factor and E0 values obtained from Artemis analysis, or you can try to repeat reverse Monte Carlo simulations with different values of these numbers and find the structure models which gives the best possible agreement. All these approaches are sometimes useful and sometimes necessary. All right, so if you look again, what else happens with the output, then after this first information, you can also see the list of scattering passes, which are included currently in the calculations. And you can see that includes 3 single scattering passes with average distances 2.4, 4.0, and 4.7 angstroms, and with 4 and 12 atoms in these corresponding coordination shells. And we also include 3 double scattering passes, all with the length 4.45 angstroms on the 12th neighbor. And there are 12 passes of this kind of type around each absorbing germanium atom. And finally, then once all this preliminary part is done, then the EVAX prints out the status update after every 10 iterations, and you can see this number is current residual between experiment and simulations, and hopefully should see that it reduces after each iteration, or it should either reduce on average, and at some point it should reach more or less low value, which would indicate that the spectra in your theoretical model matches experimental data. All right, so this is, I think, still working. It's a work in progress. We can look now on the output files which are created. So there are a lot of text files with outputs created, and they contain, of course, the spectra for experiment, simulated spectra, and they contain Fourier transforms of experimental spectra and theoretical spectra, and you can look them also to monitor the progress of your simulation. So if you, again, there are some simple GNU scripts here to facilitate the visualization of this data. And you can look now how the Fourier transform for simulated spectra matches the experimental one. So experimental data are shown with blue, the simulated data are shown with red, and you can immediately see that already after these 700 iterations, the agreement in experiment and simulations is actually quite nice. I think we are halfway there in our simulations, but already we see that this model gives quite a good agreement. Another important files to look at is these files with XYZ extension. These are containing the initial structure, which is constructed based on this P1 file, which I discussed, and this final structure model or in this case, current structure model, because it's not really final yet, the current structure model of this crystalline germanium. So if you look at this initial file, we can again open it with Vesta. So it's quite boring cubic structure. So all the atoms are in the perfect lattice spots. And if you look at now at this current structure, you will see by how much this reverse Monte Carlo model actually updated the structure model, atoms, atom positions. So again, if you look closely enough, we will see actually that now all these atoms are somewhat displaced from their initial positions, but these displacements are really, really small. And this is what this is kind of expected regime where this reverse Monte Carlo methods work very nicely. So if your material is dominated by the thermal disorder, then these reverse Monte Carlo simulations will be really able to find very good structure, which gives you very good agreement with experimental data. So basically, the whole objective for this reverse Monte Carlo simulations, in this case, is just find this very small, relatively very small displacements for each of the atoms in the model, so that the calculated averaged XAS spectrum matches well the experimental data. And again, these are not huge displacements we are talking about, but something on the order of below 0.4 angstroms. All right, so this is about the structure.
So I have a short question. So whatever we see is a instant photo of the structure, right? Like
yes. So the final structure is the one that should be the one that will be representing the time and spatially averaged signal which you have in your experimental data.
So in reality, it would rather be a cloud rather than a single point atom displaced from its position.
So here the structure, as you saw, it's a relatively big set of atoms. So it's a relatively big supercell, and each of these atoms are displaced by its own displacement vector. And the final structure is just the average. When we calculate the spectrum, which we compare to the experimental one, we just calculate exospectra for each of these atoms in this big supercell. So we do only averaging over space. We don't really have any time average. But we, of course, assume that in all the normal materials, averaging over space should be equivalent over averaging over time.
Mm-hmm. Yeah, we had a couple of questions about the applicability of RMC.
Yes.
People are asking if RMC would work in case of the particles absorbed at some surface, like the nanoparticle on a substrate.
Yes. So again, the question is how to create this initial structure model. If you have some nice guess how this particle may approximately look like, absorbed on this support, there is no reason why not to try to optimize these reverse Monte Carlo simulations. And we had some experience with modeling particles which are strongly interacting with the support, platinum nanoparticles and titanium oxide support. We were able to find such structure model which fitted experimental electrons data quite well. But again, the crucial point in these situations is to find this initial structure model. I think in this case, like DFT simulations can be quite helpful to get your initial guess, and then you further optimize it with these reverse Monte Carlo simulations to get really good agreement with XAS.
Yeah, and another question was about the doping. If in strontium molybdate, if like we substitute molybdenum by cobalt, then it distorts the structure seriously. Yes. So what RMC help in this situation?
So we did also calculations like this, and the point here is that this initial structure model corresponds to quite a big supercell in this case. So if you have 10% of doping, for example, you create a huge supercell and you then randomly select 10% of atoms which you replace by these dopant atoms, and then you try to optimize this big structure model which contains not so many dopant atoms, and it works actually. So
so you said huge supercell. How many atoms should there be in this cell?
Yeah, so typically it's a very good question. So typically I would say you need to have about between 100 and 1,000 atoms of absorbing type in your model. Mm-hmm. So if you have dopant concentration of 10%, you would want to have at least 100 of dopant atoms, and then you can calculate how big supercell is needed to accommodate this amount of doping atoms. So in principle, of course, the more atoms you have, the longer all the simulations will take, but there is no really physical limit on how many atoms you can have in your model.
Mm-hmm. So I know you modified FEF code to include more atoms into the cluster, right? The cluster size. Is it important for those who would use it every day, or it was done for some specific problem?
So it is. So this AVAX works with this F85 Lite or 8 Lite version, and for some reason they decided they want to keep the number of atoms in their model below 1,000. So if in your structure in together is less than 1,000 atoms, then this original FEF code works fine without problem. And it's for many applications, it's fine. As I said, this amount of absorbing atoms should be like between 100 and somewhere below a few hundreds. So it may work for many cases. For some cases, it will not be sufficient. But again, it's not so complicated to update this FEF code. And actually, this examples folders contains the updated FEF code version. So if you want to use it, you can just take it from one of these example folders. Yeah, this one is already updated.
It's Windows only. That one is compiled for Windows.
Yes, but again, if you want a Linux version of this FEF code or a Linux version of AVAX code, it's also available by request. Just send an email.
Mm-hmm. Okay, thank you. And one question regarding the experiment on uranium trioxide. What was the range of experimental temperatures?
So it was several experiments. We had low temperature data for uranium trioxide. We have high temperature data. I think we went up to up to like 600 kelvins, because then it decomposes those temperatures. But in principle, we are mostly very interested, I guess, in the low temperature data in that particular state. So we studied from liquid helium temperature up to 600 kelvin.
Thank you.
All right, so I think our calculations meanwhile are finished, hopefully. Yeah, they should be finished. And basically, yeah, you can have just a final look at how the agreement between experiment and simulations look like. So yeah, it's nearly perfect for this particular simple case. And maybe I will just point attention to two more useful things we can plot immediately. So one thing is to plot contributions of different scattering passes to the total signal, which is important if you, for example, want to use reverse Monte Carlo simulations as some kind of guidance for conventional XAS data fitting, because then you can figure out which passes are more important for simulations and which are less important. And finally, of course, you can also look at this Bonnard distribution function, this other distribution function, which is also outputted after reverse Monte Carlo simulations. And you can see distributions of nearest neighbors within the first coordination shells calculated from this final cloud of atomic coordinates, and you can immediately access it and analyze it. All right, so there I will probably not go into much details about other examples. You can try them by yourselves. All these instructions are given for each of them. So the gold 28 example is example of gold nanoparticles covered with some sulfur atoms. And this is also a quick example, which can also run within about 30 minutes or half an hour. And then this example of cobalt tungstate is the example I briefly discussed in my presentation. So it's cobalt tungstate nanoparticles. And we do analysis simultaneously of cobalt KH and tungsten L3H. And this simulation takes about 10 hours to complete, to finish. And then this example of rhenium trioxide also is included, and it's, I think, about also 10 or 12 hours of simulations on a normal Windows machine. So you don't really need to necessarily have a very powerful Linux cluster to run this. They work very nicely on Windows machine. You can just leave them overnight and with Monica Cannon.
So, but in principle, it can be parallelized, and if you have a multiple
so it is parallelized, yes. So if you have more than one core available on your desktop computer, or if you have more than one core available on your Linux machine, then yeah, you can benefit from that. So it's not super well parallelized. So if you increase the number of cores two times, it will not be 2 times faster, but it will still be faster than on one core. So. It makes sense to increase the number of cores maybe up to 16, I guess. I would not try to do more than that, because then this improvement is really negligible. So it's not really designed to run on like 200s of cores, but it's designed to run well on a small number of processors.
Right. And we had a question about the language that was used to write this code. And I would add another question: is the source code available for compilation and downloading, or it's?
Yeah, so it's written in C++, and source code is available again as the same as Linux version of request. And my email, I will share it. I mean, I've shared with many people. So far, there were not many complaints.
All right, thank you.
All right, so if there are not many questions, perhaps we can move to the second neural network part, or how we are doing this time.
Well, I think people have to try and run it, and as you mentioned, it may take quite some times. But yeah, there's a question if it's parallelized by default, or you need some extra measures like MPI running.
All right, so it does not really using MPI. It's using this multiple threading approaches. So I will, and it's actually, yeah, if you open one of these input files for this germanium thing, which we looked at. So then there is one last parameter, number of threads, which here specifies that we'll try to run on 3 threads. And then all this parallelization will be done by your operating system, basically. So in my computer, in this case, it's my laptop. I have 4 CPU cores available, so I can run on 3 or 4 threads if I want it, and it will work fine. So it's, yeah, so you don't really need, if you want to run it in a parallelized manner, just increase this number, set this number to the number of processors you want to use for your calculation. It's quite simple.
And yeah, a question that we get to most of the codes, if there's a GUI of some sort to prepare the input files.
So as I said, it's a text line, it's command line program. There is no really GUI as such, but I really tried to keep this input relatively simple and straightforward. So all these text comments, as I mentioned, you don't really need to have all these parameters specified. You just need to specify the ones which you want to change, and others will be used by default. And typically, you will want to change your name of your input file, the name of your structure file, and the answer may be fitting ranges in K space and R spaces. So there are really not so many parameters to change. All these technical parameters you typically don't really want to modify unless you know what you're doing.
Yeah, so the general recommendation, general recommendation is to take the example and modify it to your own needs.
Yes, and as I mentioned before, from this web page, you can find many more examples. You can find the system which is the most similar to yours, and in any case, it makes sense to start with that, to run simulations for this system for which you know that RMC works well, and then try to modify it to adapt to your needs. And regarding the outputs, yes, outputs again are the text files. You can be plotted in whatever you want, in Origin, in Excel, here I'm using GnuPlot for plotting, but yeah, of course, it's your choice and how exactly you want to plot this data. All of these parameters are described in this user manual, which is also should be more or less updated and contain all this description of all parameters and all files, and again, try to keep it more or less simple and accessible to everybody.
Okay, so if there's no more question, then maybe we can go on and proceed to the machine learning.
All right. Yes, so I will try to close all the open windows so that okay, this one will also complete. All right, so again, it will be first some kind of theoretical introduction, and then we'll go to a practical example. And so I will be discussing applications of machine learning. It's another way how to analyze X-ray absorption data. And in the second part of this talk, I will come back to EXAFS data analysis, but in the beginning, I would like maybe to talk a little bit about XAS analysis and why do we want to do it and how we can do it and how the machine learning can benefit, can help us for these purposes. So again, EXAFS and XAS contain complementary information. They're both basically, the physics of their origin are similar. So again, talking about the interactions of a photoelectron scattered on the neighboring atoms around your absorbing atom. And again, both the EXAFS and XAS are sensitive to the structure of the material. And for example, if you plot different EXAFS spectra for particles of different sizes and different shapes, they are clearly different. So typically particles which has larger surface to volume ratio has a lower amplitude of EXAFS oscillations, and similar feature can be seen also in the XAS spectrum. But again, smaller particles tend to have this more featureless XAS spectrum. So again, the question is how to extract this information from the XAS spectrum, and this is a problem which is more challenging than in EXAFS data analysis. At the same time, there are situations where XAS is really the only thing that we have, because especially if you talk about measurements under in situ or operando conditions, sometimes it can be quite challenging to measure good quality EXAFS. But usually, XAS data are usually available because they have the oscillation amplitudes are larger in this range, and also they can be measured much more quickly. And again, the problem, of course, is interpretation, because if for EXAFS you have this nice fitting formulas available, then for XAS they don't really exist or don't really work so well. This is illustrated on this example of platinum foil. So black dots show experimentally measured XAS spectrum for platinum, and then the results of simulations with two codes, FDMNS and FEF, which should be already familiar to you, are shown with red and purple line. And basically you can see that both of these codes have some quite significant systematic problems in some. So qualitatively they match these oscillations in experimental data, but quantitatively some amplitudes can be quite different. And dependently how you do the background subtraction, you can make this agreement more visible or less visible, but the problem still exists. Which means that all this, if you would try to use the reverse Monte Carlo fitting of XAS spectra instead of EXAFS spectra, it would give you some answer, but it will probably not be the correct one, because if you try to optimize the spectra too much, in this case, in terms of try to remove the disagreement in experimental simulations too much, you will be fitting these systematic errors instead of fitting your experimental data. So since these theoretical simulations are not so working so well for XAS spectra, so there was, during the last decades, when you analyze XAS spectra, the tool of choice usually are things like linear combination analysis, where you basically try to find such a combination of spectra for some standard reference materials so that the linear combination fits your experimental spectrum. And for example, if your material is a mixture of oxide and nickel and the metallic phase, you can fit your experimental spectrum with a linear combination of reference spectra for your metallic foil and metallic oxide. And then you can extract fractions of how much oxide and how much metal is in your material and how it changes its time. So this kind of archetypical way how to do XAS analysis from in situ measurement. And the problem here, of course, is that it works fine if its a sample is simple mixture of bulk-like materials, but if you try to use this method to analyze something less defined, for example, nanoparticles, then you quickly run into problems. For example, this reference spectra for bulk materials are known, but for nanomaterials, not so much. And especially because all these nanomaterials tend to change in the reaction conditions and in different environments, they tend to interact with adsorbates, with the surface, with substrates, with ligands, and all this affects the structure, and all this affects, of course, also the XAS spectrum. Moreover, especially if you talk about small nanoparticles, you need to be aware of that, again, experimental measured signal is an average from all sites which are present in your sample. And of course, some sites on the surface of the nanoparticle and sites in the core of the nanoparticle have a different environment, and they quite differently contribute to the absorption spectra. And if you would try to use some linear combination analysis, you would need to know separately what are the sites, what are the spectra for each of these different sites, which of course is experimentally not very feasible thing to extract. So at the same time, there still are indications that there is this useful structural information in XAS spectra. And if we focus again on this problem of the fact that different sites give us different contributions to the average signal, we can use some, again, FEV code or DMS code to model these contributions of different sites. And you can see that indeed sites with low number of neighbors have this featureless spectra, while the sites which are located within the core of the nanoparticle have more bulk-like XAS fingerprint. And as a result, when we do the averaging over all the entire nanoparticles, samples which has contain only surface atoms, so some particles with a large surface to volume ratio will have again this smooth and featureless spectra, while big particles will have this spectra which are similar to what we see in bulk. So at least from theoretical simulations point of view, there should be a possibility to distinguish between different particle sizes. And we see also the same trend in experimental data. So this figure below shows the experimental XAS spectra for platinum nanoparticles of different sizes. And we indeed see that some systematic trend in how this oscillations changes of this particle size. So information is there, how to extract it again. When we believe that supervised machine learning methods or artificial neural networks can be a really good tool here, which could be really beneficial for analysis of XAS spectrum. So what is the idea behind the supervised machine learning? The idea is to find some mathematical model which, based on some set of training points, would give you predictions for the points for which you don't know the experimentally determined value. So basically, we want to find some relationship between some inputs X and some outputs Y. And yeah, you can call this inputs features and the outputs as some structured descriptors. But the point is to find this more or less smooth mathematical model which will describe this relationship. And of course, normally you can use some kind of polynomials to fit this relationship between inputs and outputs, or you can use some more complex mathematical functions. And in case of artificial neural network method, this more complex mathematical function is a composite function which can be represented as a network of nodes, where each node is doing quite simple thing, just adds all inputs with some weights theta, and then produces a single number, which can be similarly processed by the nodes in the following neural network layer. And the advantage of neural network approaches is that you can easily increase the complexity of the model just by adding more and more nodes and more layers of these nodes to the architecture of your neural network. So if you start with very simple neural network with no intermediate layers at all, you can fit only very simple linear relationships. But if then you increase the number of nodes in your neural network, you can at some point find such model which could adequately describe arbitrary relationship between inputs and outputs. So that's the basic idea. And the difference here, well, not the difference, but in our case, inputs are XAS spectrum. So it's not just one X variable, but it's 100 data points in our spectrum, for example. And the outputs should be some useful descriptors of particle structure. And such useful descriptors can be, for example, coordination numbers, again, in the first few coordination shells. And why the coordination numbers are useful descriptor? Because first of all, it's easy to compare them with what you can extract from EXAFS. And also because we already know how from the coordination numbers you can determine particle size and particle shape, because there is like decade-long history of determination of particle sizes and shapes from coordination numbers from EXAFS data analysis. And the point is, again, if you go to larger and larger particles, number of surface sites relatively decreases, and the average number of nearest neighbors increases, and you can exploit this relationship to figure out what is the size of your nanoparticle. And if you have access not only to the first coordination shell, but also to the more distant coordination shells, you can also figure out what is the shape of your nanoparticle if you know the coordination numbers. So that was the idea here. So the point is, okay, so how we have this novel general idea already, how we can implement it in practice. And basically the main question to answer is how we construct this training data points. So how do we get such significant amount of spectra for which we know what is the correct corresponding coordination numbers or corresponding structure? And clearly it's not really feasible to do it based on experimental measurements, but again, we can try to use theoretical simulations, while keeping in mind that these theoretical simulations are not really perfect. But maybe they're good enough for this machine learning training purposes. So the idea here was to generate XAS spectra for particles of different sizes and different shapes, and then use this database of spectra and corresponding coordination numbers to train neural network to optimize this neural network weights, so that then when we as input provide experimental spectrum, we can also get some coordination numbers which hopefully are somehow representative of the spectra of the sample that we are analyzing. And this idea actually worked very well. So we applied it first to platinum nanoparticles. And this slide basically demonstrates one of the results which we'll be also getting during this demonstration session, basically that if you train this neural network using theoretical data and then provide as input, again, some theoretical data which were not used for training, then the neural network will provide for this validation set or the control group, control set, also answers which are quite close to the true coordination numbers in this in the respective data set. But this works only if you use sufficient numbers of training examples. So on how many how many training examples do you need? It actually depends on how subtle is the fingerprint of the corresponding structural characteristic. But for the first coordination shell, if you're interested in the only in the number of nearest neighbors, you can see in several hundreds, maybe of examples to determine reliably this coordination shell, coordination number in the first coordination shell. But if you want to see more subtle things like the a number of neighbors in the fourth coordination shells, and you would need a significantly higher amount of training examples available. Basically, the limit here is hundreds of thousands of training examples, and the limit here is imposed by the memory of my computer, because if I try to have more than 100,000 or 200,000 training examples, then I'm running out of memory, basically. And, but the more examples you have, the better it works, and the better are the performance of this machine learning scheme. The point here, the critical point, which is often overlooked in many publications about machine learning, is that this final neural network should work not only with theoretical data as input, but also importantly with experimental data. And since we know that there are the systematic errors between experiment and the simulations, we really need to be careful or really need to pay attention to this step. And for this platinum nanoparticle, we did this validation again using platinum nanoparticles for which we knew already from EXAFS what are the correct coordination numbers. And we were able to demonstrate that these coordination numbers which are getting from XAS really match those from EXAFS, which was big relief, and basically the whole point of these papers, of this original work about machine learning applications for XAS data analysis. And yeah, we will revisit this example during this practical part of this talk about artificial intelligence. Then the next step, okay, we obtained these coordination numbers, so what, then what? And the next, how we determine the three-dimensional shape of the nanoparticle from these coordination numbers. And here we simply just compare these coordination numbers for the first four coordination shells with a large database of calculated expected coordination numbers for particles of different sizes and different shapes. And we are looking for the shape and size which would provide the best possible agreement with these results of neural network analysis. So again, these are this slide lists these coordination numbers for different platinum nanoparticles determined from neural network-based analysis of experimental data, and here we show corresponding best fitting shapes. Of course, the larger is the nanoparticle, the more ambiguous this analysis gets, because more and more different shapes and sizes can fit the set of obtained coordination numbers. But if the particles are really small, 1 nanometer and smaller, then in this way we can get a more or less reliable estimate of how the particle shape may look like. In the context of my previous talk about reverse Monte Carlo, it's actually useful that we can validate the shapes using EXAFS data and reverse Monte Carlo simulations where such EXAFS data are available. Basically, in this particular case, we used these models constructed based on neural network XAS analysis and use them as input for reverse Monte Carlo simulations, and we're able to demonstrate that after this reverse Monte Carlo optimization, the obtained data really matches experimental one. This kind of nicely demonstrates applications both of neural networks and reverse Monte Carlo simulations in a single story. It's not only, of course, about platinum nanoparticles. We have applied since this original work also to study many different systems. One interesting example was copper clusters, which were size-selected copper clusters, soft-landed on different oxide supports. In this case, we are able to demonstrate that using the same or similar approach and similar neural network, we can extract information not only about the particle size, not only about the coordination numbers, but also about the average interatomic distances, because these also are affecting quite significantly the appearance, the shapes of your XAS features. So we can use, so whatever parameters of your part material structure do affect your XAS spectra, they in principle can be extracted by the same approach, with the same neural network, providing that these effects can be modeled sufficiently reliably using existing codes for ab initio XAS model. And one of the recent examples was a study of, again, platinum nanoparticles, but using polarization-dependent X-ray absorption data. So here we had XAS spectra collected with different polarization, and this was quite a bit unusual system for X-ray absorption studies, because these were not powder-supported particles, but nanoparticles supported on single crystals, on a single crystal titanium oxide surface. And we benefited from the fact that the sensitivity of X-ray absorption spectra depends on the for two different bonds. Sensitivity of XAS spectra of different bonds depends on the angle between X-ray polarization and the bond orientation. And if you can collect the data for these highly oriented samples with different polarizations, you can directly probe the anisotropy of particle structure. So we had 3 different XANE spectra collected with 3 different polarizations. We processed them, all 3 of them, using neural network. For each of them, we obtained the sets of corresponding coordination numbers in the first 4 coordination shell, and then we try to find such a structure model which would fit all these 12 coordination numbers in the best possible way. And this was the final answer, which was nicely enough also validated by microscopy measurements for this system. So this is kind of illustrates how this machine learning method works for XANE's data analysis. Of course, we had also idea to see whether we can apply it to EXAFS data analysis. And the idea here was, again, let's try to use entire EXAFS spectrum as input instead of XANE spectrum and try to determine some useful descriptors of particle structure. Since determination of coordination numbers from EXAFS spectrum is not very interesting, because it can be done by a number of different methods, including conventional fit fitting, we decided to see whether we can extract the entire radar distribution function using this neural network-based approach. So again, we keep the same idea as in a XANE study. We use a spectra as input, and as output we have a structure descriptor. In this case, it's a histogram of bond lengths. And so the number of bins in this histogram correspond to the number of neural network outputs. And then we use theoretical structure models to do the training, to establish these weights of neural network nodes. Important difference between XANE's and EXAFS analysis is that EXAFS is sensitive to thermal disorder. That's why we cannot really use static models, but we need to use some moving dynamic models. And for this purpose, we can use molecular dynamics simulations. And for example, here we demonstrate that for quite broad range of different copper oxides, these molecular dynamic simulations actually can give quite decent agreement between experimental EXAFS and simulated EXAFS. So but of course, this agreement is not perfect. Nevertheless, we hope that it's good enough for our neural network method to be trained on this data, and it actually appeared to be really the case. So we use this structure models obtained from molecular dynamic simulations and corresponding theoretical EXAFS spectra to train neural network, and then apply this neural network to extract the radar distribution functions from EXAFS spectra for these reference materials. And here we compare this radar distribution function extracted by neural network with those from reverse Monte Carlo simulations. And you can see that they matches quite perfectly for these reference materials, which kind of independently validates both neural network and reverse Monte Carlo method, which is very nice to see. So question is, why then we do need 2 methods if they give the same answer? The answer to this is that reverse Monte Carlo is working very well for these bulk materials, but with neural networks, we can actually access a more challenging case where we have coexisting different phases or mixtures of different phases. And, or for example, where we need to address particle size effects. So all these situations are better addressed by neural networks rather than by neural network methods. And just one case study here to illustrate this concept. It was a study of copper zinc nanoparticles used for electrochemical CO2 electroreduction. So here we prepared copper zinc nanoparticles with different copper to zinc ratios, and we observed that the products into which CO2 is converted actually depends quite significantly on the copper to zinc ratio. What is more interestingly, here we also saw that this product distribution changes with time. For a particle with 1:1 copper to zinc ratio, at the beginning of the reaction, we're producing mostly methane as the main CO2 reduction product, but at the end, it's mostly hydrogen. So there is some time-dependent changes in your system as well. And we wanted to use EXAFS data analysis to figure out what's going on here. So before we went to EXAFS, we actually looked at XANE spectra and did some simple linear combination analysis. And we observed that in as prepared state, these copper and zinc in our nanoparticles are completely oxidized, as shown by red lines in this figure. But under reaction conditions, they are getting both reduced because the final XANE spectra are quite similar to the spectra of metallic copper and metallic zinc. But what's interesting, if we do this linear combination analysis, we can see that the rate with which copper and zinc are reduced are quite different. So copper is reduced almost immediately, while for zinc, it actually takes several hours and the reaction conditions still gets completely metallic. So the natural question to ask is what happens with copper environment during the slow reduction of zinc? And we try to answer this question using reverse Monte Carlo, using neural network methods. And we used this experimental EXAFS as input for a neural network, and here are shown the reconstructed radial distribution functions. So magenta line shows the copper-oxygen contribution, while the blue lines show copper-metal contribution, which can be either copper-copper and copper-zinc. The important point here is that because copper and zinc are neighbors in periodic table, even with neural networks, we cannot really distinguish between them. But at the same time, we still can hope to distinguish between copper-rich and zinc-rich materials if we are able to extract accurate information about interatomic distances, because this is expected to be different in pure copper or in copper-zinc alloy material. So this all boils down to whether we can use neural networks for accurate determination of interatomic distances in our nanoparticles. So, and indeed, these radial distribution functions obtained from this neural network analysis are containing quite interesting information. So in as prepared state, or nanoparticles, the Bonal distribution functions there looks pretty much as the Bonal distribution in copper hydroxide. So we have this strong copper-oxygen contribution, some contribution of copper metal in the second coordination shell. So, but overall, it's quite a good agreement between these two structures. Immediately after we apply potential, the copper-oxygen contribution is gone, and we are left only with copper-metal contribution. But interestingly enough, that's not the end of the story. So if you look carefully enough, you can see that after 7 hours, there is shift of all these peaks in radial distribution function. And again, this effect is much better visible if we have access to more distant coordination shells. You can see the shift is more pronounced in distant coordination shells. And what's also important that the shift actually is consistent with the difference in interatomic distances between copper foil and copper zinc brass alloy foil. So what we see here, this shift is actually indication that gradual alloy formation takes place in this nanoparticle. So if you follow how this interatomic distance around copper changes with time, you can find actually a very good agreement on in terms of time scales between these transformations and the transformations in the catalytic properties. So basically, we believe here that what happens with this material that immediately after we apply potential, we have our catalyst is actually mostly pure metallic copper with some inactive chunks of zinc oxide in it. And this copper is producing methane as the main reaction product. But then, as the reaction proceeds, copper and zinc form alloy, and this copper-zinc alloy has completely different catalytic properties, and as a result, also the selectivity of our catalyst changes, and now the hydrogen is the main reaction product. Yeah, so this kind of study demonstrates why it's important to have this access to distant coordination shells and why it's useful to have neural networks when we need to analyze spectra for mixtures or for samples with coexisting different species. Basically, to summarize this part, so again, machine learning is a nice tool how to analyze both XANES and EXAFS spectra. And again, we can use it to address these common challenges in EXAFS data analysis, such as analysis of further coordination shells or analysis of strongly disordered systems. And we can get structure descriptors and apply this method both to study of crystalline materials as well as less defined systems such as disordered materials, nanomaterials, or mixtures of different phases. So important additional advantage of neural networks is that they work very well, very quickly. So analysis can be done within seconds. So if you reverse Monte Carlo, will take, as I told you, like 10, 12 hours to get your answers. Then with neural networks, you can get your answer within seconds. And of course, it means that you can analyze large sets of data. Moreover, since in this case used for training some realistic structure models obtained from multidynamic simulations, it introduces indirectly additional constraints in your analysis, which means that the structures which you're getting as a result of neural network methods are always, at least to some extent, physically meaningful, which is not necessarily the case with reverse Monte Carlo simulations, which only guarantees that the structure is geometrically meaningful. But again, of course, neural networks have also some drawbacks. And one problem is that if you're structured your for which you collect experimental spectrum is too different from the structures which you use for neural network training, then you will run into problems. You will get some answers from neural network, but they will be quite meaningless, and it's also another danger of neural network method or machine learning method is actually when you get your answer, it's really hard to estimate how sure you are about this answer or how certain you are that this really is the structure which was inside your sample. Because if in the reverse Monte Carlo method, you can always validate your structure model by just looking at, by comparing final experimental XAS spectrum with final theoretical XAS spectrum. In neural network, you're just getting the answer and that's it. And there is no really direct, at least, associated uncertainty with it. In any case, we can still identify several regions or several applications for machine learning. And I think from my point of view, the ones that work very well, the cases where machine learning works very well is the cases where we have mixtures of well-defined materials or materials where we need to process a lot of different spectra within a short time, which, like, for example, maybe large sets of time-dependent or spatially resolved EXAFS spectra. So important applications also is XAS analysis, because there it seems, at least so far, that machine learning methods can perform much better than all kinds of fitting-based approaches, partially because they are able to address this systematic difference between simulated and experimental data, or at least are not so sensitive to it. Well, and of course, important to remember that if your material is too different, you always need to know what kind of structures were used for neural network training, because if your material is too different from this neural network, from these training structures, then you have the danger that your answer that you're getting is not really, physically meaningful. And again, you have also the access to this presentation afterwards. So you can, if you're interested, you can look into this into these publications, where we discuss these methods both for in terms of XAS analysis and for EXAFS analysis in more detail. Yeah, and I will also maybe use this opportunity to say thank you also for all my collaborators from all my previous institutions, from the University of Latvia, from Stony Brook, and from Fritz Haber Institute, because of course they're also helping a lot for developing and validating these approaches. All right, this I think is another good point for questions and answers before I move to the practical part. I think there are some questions.
So I was wondering if the output that you get from the neural network is just a number, or it's there's some probability for this number.
Yes. So the way how we estimate uncertainties is we train several neural networks on different training data. And if we see that the prediction of these neural networks are very different from each other, then it means that there is large uncertainty, large error bar, and it means that these structures that we have may be not very well represented in our training sample. So there is ways how to assess this uncertainty or certainty about neural networks, but you just need to do some extra steps for that. In our particular case, the simplest way is just to like repeat training 4 times or 5 times or 10 times and compare the predictions of 10 different neural networks.
You see,
that's not the only way how to do it, but that's the way how we usually do it.
So yeah, I was thinking about this image recognition presentation where there's a bar showing it's 90% airplane and 60% a kitty and so on.
Yes, so we can do something like this also with our approach. Just in our case, the probability interpretation will be that 9 out of 10 neural networks agree that it is oxide, and 1 out of 10 neural networks that it's metal or something like that.
So there's a question if there's a source of training data that can be used. So in your case, you generated a lot of theoretical spectra from FDMs, right?
Yes.
Mm-hmm.
So we cannot really use experimental data, at least for neural networks, because as I mentioned, you need hundreds of thousands of spectra available, and there does not exist such large database of experimental spectra which would allow us to use experimental data for training.
I'm wondering if all this fast scanning routines and fast scanning beamlines that generate maybe 100 of spectra in a minute would help to educate.
Yeah, so the main issue is actually not the fact that it's slow to measure experimental data. The main challenge is that you need to know and be sure that is that what is the structure, what is the correct structure of your material. So if it's bulk material, of course, you can do it, but then there is not so many interesting questions to answer. But for example, if you want to determine a particle size from your XAS spectra, so you would need to tens of thousands of experimental spectra for particles of different sizes. So you would need to figure out how to generate 10,000 of samples with very well-defined particle sizes, which you know very well what they are. And then you can hope to use this database for neural network training. So this is just not feasible, not just because it's slow to measure experimental data, but just because you don't really have the certainty about what's exactly inside your sample. It's sufficient.
I see. Thank you. And our question is whether it's possible to estimate the Debye-Waller factor, or I will ask for myself if there's any other parameters other than the coordination number.
So as I said, in case of EXAFS data analysis, we extract entire data distribution function. You can estimate whatever you want. Interatomic distances, Debye-Waller factor, just by integrating this data distribution function. Or you can also train your neural network to directly predict this Debye-Waller factor. If the question is about XAS analysis, I think it also should be possible to some extent, but you need to be aware of that XAS is actually not very sensitive to the Debye-Waller factors. So it is sensitive to the number of nearest neighbors and the number of and the average interatomic distances, but it's not so sensitive to the disorder, and that's actually the whole point of using XAS instead of EXAFS. So you can try, but it will be case specific, and probably it's better to use EXAFS for this rather than XAS.
Hey, thank you. Yeah, let's proceed to the demo then.
Yes.
We're perfectly on time.
So for demo, just get some water. So all that you need for a practical example of a demonstration of this neural network method is located in the directory machine learning demo. And maybe I will quickly introduce what's inside. So here is some notebooks for Wolfram Mathematica, which is the tool I'm using here to run this example. So maybe you heard already in the beginning of my discussion with Roman that in principle you can do, there are many different tools available that can do this machine learning for you. So it can be Python-based solutions like TensorFlow or CLS. It can be MATLAB, it can be Mathematica, and they both work fine because we don't really need very complex machine learning models for our purposes here. And in fact, also there is no really also difference in terms of speed or memory consumption or accuracy that you're getting if you use Python or if you use Mathematica. And yeah, I prefer to use Mathematica just because it's more convenient for me. And I also think it's really a really great tool that anybody should be like, at least try it for him or herself, because it's really amazing what you can do with this program, not only in terms of machine learning, but in general in data analysis. All right, so there are some README files which describes what are these files which are located in different directories. So if you go on this and then XAS data directory, then there are some files which contain experimental data, experimental XAS spectra for platinum nanoparticles of different sizes and different shapes. They all are measured in hydrogen on aluminum oxide support. And then there is another directory, nanoparticles, which contains calculated XAS spectra for particles of different sizes and different shapes. So there are 18 different particle models. So if you open this first folder, you can see that it corresponds to the platinum nanoparticle with 13 atoms. So if you plot it, so it's just a octahedral arrangement or closed packed arrangement of platinum atoms. So one atom in the core, 12 atoms on the surface. So in this structure model, it's easy to see that there are two non-equivalent platinum sites, one in the center and one on the surface. And that's why we have these two additional directories here. So 1 and 2. One is containing XAS spectra for one non-equivalent site and another is for the second non-equivalent site. So here, if you go to this first directory, there is another XYZ file where this actual absorbing atom is highlighted. So this one case is the central atom in this 13 atom cluster. And in the second directory, you can see that you can access it somehow. In the second directory, there is spectra calculated for the surface site in the same cluster. So, and every of these directories contains input files and output files for FEF and FDMNS-based XAS calculations. So if you had some experience with FEF and FDMNS before, so you more or less should be able to follow out what's inside this input file for FEF and FDM file for FDMNS. I will not be going into details in that. So here, basically, I will use directly the result of the simulation. So XAMU file contains just a text file containing calculated XAS spectra using FEF. And then there is a similar file out of DMNS, which contains output of FDMNS simulation. And basically, the most annoying part or most time-consuming part of machine learning based on also XAS and EXAFS spectra is to organize all these folders and directories so that we can keep track of which spectra corresponds to which site, and then we don't get lost at some point, which is like super important for this machine learning applications. Everything else is relatively easy and straightforward. All right, so this machine learning can base this Mathematica file, which contains this story which I'll be going through, and then you can also look directly at this expected output, which is this executed version of the same machine learning notebook, but we will get there during this practical demonstration. So I'm opening this notebook with Mathematica version 12. Everything above 11.3 should work also. Maybe there are some small differences in formatting, but yeah, I will enable that. And yeah, it should be also relatively self-explanatory. All these files there are minimize a little bit. So there are all these comments and descriptions of what's going on are provided here. And I will execute just all these cells one by one, and we can discuss what's happening. So I will just first execute some preliminary functions. And again, you don't really need to be expert in Mathematica to use this notebook. Because, I mean, all the important points are highlighted by red color, so you can pay attention to that. And also all these comments are provided. So the first step, since we will be using theoretical simulations for neural network training, which we then hope to apply for interpretation of experimental data, is to validate how good actually these simulations are. And for this, it's always good to have some reference calculations for well-defined materials, such as bulk platinum in this case. So the first step will be to import calculated XAS spectra for bulk platinum metal and compare it with the experimental data. So I execute this, and hopefully it works, and it does. So the black line is the results of experimental measurements for platinum foil. The red and blue ones are the results of XAS simulations using FEF and FDMNS code. And you can easily see that yeah, there is still, as I mentioned in my presentation, there is disagreement between simulations and experiment. In both cases, FDMNS looks maybe a little bit better in this particular case, but it will be case specific. So if you go from platinum to some other metal, maybe the other way around. So there's no really way how to know in advance which would work better. And but again, we need to remember that there are other systematic errors, and we need to keep them in mind in this particular case. Right, the second step is to import all these site-specific spectra, which I discussed before. So to go through all these directories and subdirectories and collect all these structure models and the corresponding XAS spectra. So this will take a while to execute. So I will collect all the spectra, and I will randomly select 3 of them, and I will plot them, and it takes like 1 minute maybe to do it. So what this code is doing during this time, so it's not only importing all this theoretical EXAFS spectrum, but it also estimates coordination numbers for the first 4 coordination shells for each of these structure models. And for this, here for these purposes, I define coordination numbers just by looking on how many atoms are at a specified distance from the absorbing atom. So if, for a moment, I will go back to this function where I define these coordination numbers. Basically, here I just say that the atom is located in the first coordination shell from the absorbing atom if it's at the distance between 0 and 3.5 angstroms from the absorbing atom. Similarly, atom belongs to the second coordination shell if it's at the distance between 3.5 and 4.4 angstroms from the absorbing atom. And these numbers are based on the FCC type structure of platinum metal. Right, so now we can come back to these three examples which we imported. We imported everything with plotting on the three of them. And there are several columns of information. So the left column contains calculated FDMNS spectra for a particular site in a particular particle model. So a red line is the result for this site-specific calculation, and the black dashed line is the FDMNS calculation for platinum foil. Similarly, the second column contains calculations of F for the same site. And again, black dashed line is the result for platinum foil. Then the third column contains coordination numbers calculated for the first 4 coordination shells. And then there is this model with the absorbing site highlighted. So you can here see it's a cuboctahedral particle with the corner site using as the absorbing site. In the second model, you can see that this is absorbing site is the one here on the basal plane of this nanoparticle. And I think in this third model, we will not see the highlighted side because it's inside the core of nanoparticle. So we can also do some, we will also do some auxiliary things like some array interpolation because there is annoying tendency in FEF simulations that by default, all these spectra are using slightly different energy mesh. So we need to take care of that and do the array interpolation. That's a technicality. And then, we can also do some statistics and see how many spectra do we have. And it's actually 218 of them. And how we have, and some of them are plotted here in this figure. And we can also see the histograms of different coordination numbers for the first, second, third, and fourth coordination shell. So since we are dealing with site-specific coordination numbers, so these coordination numbers are always integer numbers, and they're also not really uniformly distributed or Gaussian distributed. So there are some values for which we have a lot of examples, and there are some values for which we don't really have any examples. For example, we don't really have any structure model for which we would have exactly 10 neighbors in the first coordination shell. So this is not very good situation for neural networks. So we would need to deal with this problem. And another, of course, limitation here is that so far we have only 200 examples, which is not too much for neural network training. But as I would say, using data augmentation, we can easily address this problem in this particular case. So next step will be do this data augmentation, but before that, I will do also standardization and normalization, because again, neural networks are picky about what kind of inputs and outputs are you providing. And so one point here to emphasize is that neural networks likes outputs and inputs via numbers somewhere between -1 and 1 or between 0 and 1, depending on which algorithm you're using for neural network training. So that's why here I divide all my expected outputs of neural network by these bulk values of coordination numbers, which are 12, 6, 24, and 12 for the first 4 coordination shells, just to normalize this output of neural network so that these are really numbers between 0 and 1. And then on the input side of the neural network, I do subtract from this calculated spectrum for bulk platinum metal. Again, if I look at the spectra calculated with FEF, I'm subtracting for a spectrum for platinum metal calculated by FEF. Or if I'm looking at spectra calculated by FDMNS, I'm subtracting spectrum for calculated by FDMNS. So this is basically actually the main insight where computer scientists cannot really help you, because if it would be just normal computer science problem, at this step, it would be subtracting just the average of all these training examples to normalize it, just to make sure that it's centered around 0. Here, since we want to minimize the systematic errors, or at least partially account for the systematic difference between experimental simulations, we're using this trick, where we subtract, instead of mean value of training spectra, we subtract the corresponding spectrum for platinum foil. And this is the step where you need to have some kind of insight about the specific problem that you have in mind, because sometimes it will be helpful for you. So for some other materials, it will not be helpful, dependently on how this systematic errors between theory and simulations looks like, how the background looks like, and so on. So the next step is to do this data augmentation. And the trick here is that we are taking our site-specific spectra and we are linearly combining them in artificial combinations. So inspiration for this idea is the fact that the spectra which we are analyzing, later experimental ones, is not a site-specific spectra, but is a particle average one. So we would need to average all the site-specific spectra so that we can have this particle average spectrum as a representation for experimental data. But of course, nothing really restricts us at this step to require that this average over site-specific spectrum really corresponds to some concrete specific particle. We can just sample randomly, let's say 3 site-specific spectra, and combine them in an arbitrary linear combination, and do the same operation with the corresponding coordination number, and we will have still valid relationships between spectra and corresponding coordination numbers. But in this case, we can easily, from these 200 input spectra, generate unlimited numbers of training examples. And I will show that this trick actually works very well. So basically, the next step, we're just using here only FDMNS data and constructing this 10,000 training spectra just by linearly combining these 200 existing site-specific FDMNS spectra. Okay, this is also done. So now we can also plot it and see what happened here. So our spectra, or input spectra, now on the left side. So the difference between this plot and the one on, slightly above is that, first of all, we did this linear combination trick. So we sampled 3 randomly selected 3 site-specific spectra, combined them in this linear combination, and repeated it 10,000 times. And on the right side, and we also subtracted the spectrum for platinum metal as calculated by FDMNS. So that's also another reason why the spectrum looks somewhat different. And all these right plots contain the histograms of coordination numbers after this normalization. So now they are all the numbers are between 0 and 1, because we did this division by this normalization factor. And also now they look more or less Gaussian distributed, which again is nice for neural networks. They like this kind of distributions of inputs and outputs. And again, this is a result of this artificial averaging, sampling and averaging of site-specific spectrum and site-specific coordination. So this is basically it. And the next step, we just want to create this neural network. So I will use a quite small one in this case. So it will be a neural network with 2 intermediate hidden layers and with 100 nodes in each of these layers. And again, both Mathematica and Python and MATLAB, all they have very convenient commands how to do it. So basically just one line of code where you write what is the geometry of your neural network. So you want, in this case, neural network with 100 nodes in one hidden layer, 100 nodes in another hidden layer. And of course, you have some input and some output, and the size of the input is determined by the size of your spectra, and the size of your output is determined by the number of coordination numbers which you want to determine, which is 4 in this case. You can also look how this neural network looks like. So basically here you can see that there is 4 layers, or mathematical a little bit differently, but there are four main layers in this neural network. First layer contains 129 nodes, which is equal to the number of number of data points in your spectrum. Then there are two layers with 100 nodes in each, which are these intermediate hidden nodes, which we add just to increase the complexity of the model. And then finally, we have 4 nodes, which gives us the output as these values of coordination numbers in the first 4 coordination shells. So this is one line to create neural network, and then there is another one line command to train neural network. So it's very easy. So now I will execute this one, and it will run. It will take about 1 minute to finish. So all this neural network part is really, really simple, and it's simple regardless of whether you're using Mathematica or Python. And the, again, tricky part is, again, organizing your data by different folders and then going into these folders and importing all this stuff. And it's actually more logistics than really a science. So nothing to be scared about here. Right, let's wait 1 more minute. Yeah, basically this figure shows residual between neural network predictions and true values for coordination numbers estimated from this set of 10,000 training spectra. So but during this training step, what happens, neural network optimizes its weights so that for these 10,000 training examples, which we have currently, it gives us good agreement between true values and predicted values of coordination numbers as possible. This quantity which we are plotting and which is rapidly decreasing is actually this disagreement between neural network prediction and the ground truth value.
So it says several million of examples. Where is this number coming from? In this progress bar, so 300 is probably the number of repeats, the training repeats.
Yeah, so it goes through. So we have 10,000 of unique examples, and then we go through this 10,000 examples 300 times. So that's maybe how okay. 3 million numbers. 3 million quantitative. And yes, in this case, so neural network training took about 1 minute, so not a problem. But if it's like a bit larger, you can always save it and then re-upload it again, so you don't really need to repeat the training every time. All right, so now to test how this neural network works, how accurate it is, we generate another small set of training spectra, theoretical spectra, 200 of them, again using the same linear combination trick. And we will check how well this neural network works for this 200 new training examples, which are not used for training. So this is new 200 examples. And yes, this is a similar plot to what you saw in my presentation, basically. So on the x-axis, we show the true value of coordination number, and on the y-axis, we show neural network prediction. And you can see that for this first 4 coordination shells, we really get this very nice agreement between predicted values and true values. And I just saw some quick question in the chat appearing. And yes, so this is just training was really done on laptop on just normal CPU. There was really not rigs, and it's really can be done on laptop within 1 minute. So there is no real problem of running. It's not really computational consuming. All right. And now the final step, or almost final step, is to apply it to experimental data. So here we will import some experimental XAS spectra for, again, platinum nanoparticles of different sizes. So we can plot them. So these are the same spectra which are in my presentation. Maybe background is subtracted somewhat differently, but again, you see that for bigger particles, we have more pronounced XAS oscillations. For smaller particles, we have less pronounced oscillations. So at least for the first coordination number, we know what to expect, but again, by looking by eye in the spectrum, it would be really hard to tell what's going on with the second or third or fourth coordination. And we also, from EXAFS data analysis for the same particles, we also know what are the correct values of coordination numbers. Or not correct one, but at least the ones that we're getting from EXAFS. These are also just importing here, not really doing EXAFS analysis here. But all the spectra are included, so if you wish, you can also double check these numbers and repeat EXAFS data analysis. And then, yes, apply neural network to this experimental spectra. And the important thing to remember here is that we need to process the experimental spectrum the same way as we did theoretical data. So we need to reinterpolate them on the same energy mesh. And we also need to subtract from them the spectrum for bulk platinum. And in this case, as using experimental spectrum for platinum flow. So this is this important trick, which is, I guess, allow us to address this fact that experimental spectrum looks somewhat different from the theoretical one. And here are the results. So the blue results are still theory versus theory, but the red circles are the results of neural network analysis of experimental XAS spectra. And we compare the results of neural network prediction with the results of EXAFS data analysis, and you can see they really, really nicely agree in this case. So by doing XAS analysis based on FDMNS trained neural network, we can have very good accuracy in determination of platinum coordination number, at least which we can validate here with EXAFS data analysis. So this basically is kind of concludes the main part of this presentation. But maybe we can also see what happens if we would do this training not using FDMNS data, but using FEF data. And if you may remember that FEF gave somewhat slightly worse agreement with experiment, at least for platinum foil. And we will see what happens when we do the training with FEF. So again, I will generate 10,000 training spectra. Just now this will be 10,000 of spectra of FEF calculated spectra. And I will repeat the training. It will take one more minute, I guess. We can use this minute maybe to answer some additional questions, and then I will come back.
So someone's wondering how many cores do you use to calculate that?
So this is one one laptop core. So it's really.
So it's all single, and I believe
it is possible to parallelize it. It is possible to run it on GPUs. It's but for this example, it's really not really.
That's impressive. That's impressive. And I believe it's all up to Mathematica on how to parallelize it. It's all done inside the this program. I know in Python, if you do it, you may specify manually what you use to train, where you store your data.
Here you also can specify, you just need to dig into mathematical documentation. There are some different settings that she likes to use, but we can also modify everything. So I know we did tests on GPUs and they worked really faster and they look really, there is improvement if you do the training on GPUs. But again, I mean, if it's a total training takes 1 minute, it's not really, there is not really much room for improvement, I guess.
Yeah, there's a question if the network is convolutional, but you just show the structure of the network. So it's just linear layers.
Again, we tried also convolutional networks, but I don't really see any improvement in that. And the reason is that convolutional neural networks are really good for images recognition because like specific element of your image may appear at a random place in your image. Like if you do the image recognition, you want to distinguish cat from dog, then the ear of this cat can appear in any spot on your image, and you really need to keep track on that. And that convolutional neural networks are really good just to finding ears and different spots in your image. But in our case, with spectra, we don't really expect that white line of our XAS spectra will appear in the middle of our spectra, right? So we know that the white line will always be at a specific value, a specific energy value. So all this invariance towards displacements of several different features is not really useful in this case. So we tried convolutional neural networks; they work fine, but they don't really give an improvement or significant improvement with respect to fully connected neural networks in this particular application. All right, so our neural network with FEF trained data was trained. So again, if you see the blue dots, shows again comparison theory versus theory, and there is no problem. So it's the same as with FDMNS calculated spectra, theory versus theory comparison works very well. And you see that neural network predicted values for theoretical spectra are in a very good agreement with the corresponding true values. Now, if you look at the experimental data shown here with red circles, you can see that while the trend is still reproduced, so for bigger particles, you're getting larger coordination numbers, So this is makes sense. There is like some systematic overestimation of all coordination numbers in this particular case. So it is not like completely hopeless. If you would play with background subtraction parameters and you would maybe play with FEF parameters, you probably can improve it somewhat better in this case. But the main point here is that this validation with experimental data is really a crucial step for any applications of machine learning in spectroscopy, I believe. So many papers just report this theory versus theory comparison as a result of their study, but this is really not sufficient, because if you really want to have a practically useful tool, it should really work also with experimental data. And this particular example demonstrates that, the systematic errors in FEF simulations spoils a bit accuracy of neural network predictions in this particular case. All right, so this concludes this part of presentation. So I am ready to answer your additional questions if there are such.
Well, not really. I was wondering if the same thing could be used to distinguish between different types of elements. If you just use it's similar to the wavelet analysis, where the different atoms give peaks at different case, and if the network could be learned to universally predict what's inside your compound.
So we did analysis of bimetallic compounds from XAS. So we can, it was gold palladium nanoparticles. So neural network is good enough to distinguish whether neighboring atoms are gold or palladium atoms. We can do it with XAS. Of course, it's very easy to do it with EXAFS. So there is really no, so in this particular case, it's simple monometallic system, but there is no reason why you cannot apply it for more complex heterometallic systems. And the only, whatever you can model, whatever you can include in your training models, you can also afterwards reproduce by this neural network prediction. There are some issues when you go to more complex systems, in particular how to keeping the systematic errors of modeling really systematic, but it's a rather technicality, I guess. So in practice, of course, also heterometallic systems.
And another technical question is about the number of layers and number of nodes in each layer. Is there any rules that would help to define what number to use, or it's all trial and error? So
it's a good starting. So you know already that in your input layer there are as many nodes as data points in your input spectra, and you know that in your output layer there are as many nodes as your expected output. So Node has 120 input nodes and 4 nodes in the output. And the rule of thumb usually is that for this intermediate layers you choose some value which is in between those two. So here I use 100. Which is somewhat number between 120 in the input and 4 in the output. So it's and then of course further optimization is a matter of trying and trial and error, but typically you will not really get very much improvement by playing around with neural network parameters. If it works with small number of nodes, it will work of course with large number of nodes. And you will if you optimize this number of nodes for a few weeks, you can get slightly better agreement, but it will not be like 10 times better agreement or 10 times better performance. So more important is exactly how you create these training examples, how you do this normalization, how you do the subtraction of FOIL, or you don't do it. All these things actually can play much more importance than the playing with this neural network architecture. That's why I said actually that the fact that there is this great flexibility in Python codes for changing all these optimization algorithms, number of nodes, adding some exotic machine learning features, some kind of dropout layers and batch normalizations, and all these fancy approaches, they don't really help too much in getting useful answers for most of the cases.
Yeah, indeed. I was impressed to see that a very simple network is producing quite nice output.
Yeah.
And you don't need to create anything fancy. So we have a question: if it's possible to differ, if the change in spectra are related to the particle size or to the change of the oxidation state. So in an example, it's titanium oxide, but it may be.
Yes. Yeah, definitely. So in this particular case, for training, we use only metallic nanoparticles. But if you would include in the training also oxidized nanoparticles, which we did in some follow-up papers, we can also track how the numbers of platinum-oxygen bonds changes and platinum-metal bond change. What is interesting actually in this particular example, what we tried for this pure platinum nanoparticles is that what happens if we use this neural network, which is trained only on metallic nanoparticles, and provide as input spectrum for slightly oxidized platinum nanoparticle. And what kind of answers we are getting. And apparently we are getting the same answers as we would get with EXAFS analysis. So we see the reduction of platinum-platinum coordination numbers because of this ensemble averaging effect. So in that sense, this neural network XANES-based approach reacts in the same way as XANES analysis. So if there is small contribution of oxides, you will just see the reduction of your metal-metal coordination number. Of course, if your fraction of oxide is like very significant and your spectrum looks completely different from the spectrum of platinum, then the neural network will give some crazy answers. But as soon as this oxidation or some other contribution in your spectrum is not too large, the neural networks you're using will still give some meaningful answers. You just need to be careful with how you interpret them.
So, for instance, if you take the gold nanoparticle instead of platinum with slightly different shape of the spectrum, it will not be possible to use the network which was trained on platinum to analyze the gold.
So it definitely works with EXAFS. So if I do have neural network which is trained to analyze spectra for copper, it will be likely working for zinc or nickel or other neighboring elements. So for EXAFS, there is really no problem in doing this trick. For XANES, I think it will be more problematic because spectrum for platinum and spectrum for gold are actually quite different because one platinum has white line and gold does not have white line. Despite the fact that these features after the white line are more or less the same, maybe if we account for difference in atomic distances, then there is this electronic contribution to XANES spectra. It really can be different. So it may work or may not work dependently on how much weight a neural network is assigning to this white line region. Typically, it's not too strongly looking at the white line, but I think it still will be confused by this difference in the spectra for gold and platinum.
Mm-hmm. So the advice is to train the network specifically for the compound, at least if we're talking about XANES. Yes, specifically for the compound of study, and then once it's trained, it will save you a lot of time when you start analyzing it.
So it's not just saving time. The point is that for XANES there is really no other option. I mean, there is no other way how you can analyze XANES in quantitative time. You can try to do the fitting, but I think it still needs to be demonstrated whether these fitting results are really meaningful. And I think this one is study where we demonstrated that we can get the same answers as from EXAFS from XANES data analysis.
Mm-hmm. Interesting. So if you come up to any more questions, feel free to post them on Piazza, and then these questions will be answered later. But so far, I don't see anything else. It really requires some experience, some hands-on before the questions start popping up. Yeah, so thank you, Yanis. That was really interesting. We'll have another talk of the application of the neural networks to EXAFS analysis after the break. Jeff Terry will present his results and show how they are doing this. And now we have a couple minutes to make a group picture. If you want to show up on this group photo, then turn on your webcam, and I will try to make some screenshots.
Just turn on the light on my side. It's dark here.
I believe that quite many people are using the recorded videos to later review what was said and showed during the session. And it seems quite helpful. Great. Okay, that's quite a nice gallery already. Good. Yeah. Yeah. Thank you all. We'll have a 30 minutes break, and we'll continue at 11. See you all at 11 then. I didn't have a chance to preview what you were planning to show. So I believe everything worked. Yeah, everything we were hoping for.
Well, I'm going to show the pyrochlor. We weren't able to finish the fluorides.
Oh, I see.
Unfortunately, but we're still working on it. But it is interesting. But the pyrochlor is kind of interesting. But it'll be easier for me to show it later. But yeah, no, we'll go through it. But unfortunately, we just didn't have. We ran out of time to finish the fluoride. But it was funny because I ended up making a similar spectrum to like you. When you're fitting the multiple scattering, it's really key to have them randomly oriented, because otherwise they're all together. All the multiple scattering paths are together. And unfortunately, for some reason, I didn't see the email you sent on Thursday. So had I gotten that, I might have been able to deal, but I just missed it.
Oh yeah, that's right.
Which is too bad. So we'll throw that one into the mix as well. But it's interesting because we're kind of going in the opposite direction. What do you do when you don't have training data?
Yeah, that's why I was impressed by how simple is the model that Yanis used.
Yeah,
simple model, and everything is done in minutes and seconds.
Yeah, this is not done in minutes and seconds. So this does definitely take more time. This is more akin to the reverse Monte Carlo type, the length of time. Although I'm going to do one in real time, so we'll do one in real time today during the demonstration.
So there's a question about the slides. Could you share the slides afterwards?
I can probably share a PDF of the slides.
Yeah, that's fine. Sure.
Yeah, sharing the keynote is always hard for people unless they use Keynote. So it's easier to make a PDF and share the PDF.
Yeah, that would work. So we are trying to organize all the presentations and all the data and the software that our speakers use.
Yeah.
So to make it available later.
Yeah, it might be easier to use Dropbox or something because it may be too big to email.
Yeah, right. We actually put this all onto our Beamline Google Drive.
Oh wow!
And just share.
Okay.
Okay, so.
Yeah, that sounds good. Okay. It should be ready to go anytime you want.
Right. Yeah, so let's wait for the people to return and we'll go on.
All right, so I will stop sharing maybe. Oh, there's stop sharing. Okay.
So overall, it seems to be still exhausting. That this multi-day, that this long workshop seems to be hard for people.
I don't think it's that bad. I thought it was this morning was very interesting. So I thought it was pretty good. I mean, maybe throw one more break in. We'll see how well I do because we're not allowed to eat or drink in the office. So, in fact, they had to put in special ventilation so I don't have to wear the mask during the talk. So they brought in portable HEPA filters for me today, so I don't have to wear the mask.
But you're alone in your office.
I have no ventilation though.
You don't have it.
Yeah, so in my office, they built a room where the ventilation is a hole cut out in the wall. You can't see it, but so there's no active ventilation.
Oh, I see. Okay, good. Let's start. Welcome back, everyone. We're about to start the final chapter of our workshop. It will be Jeff Terry who will tell us about the application of the neural networks to EXAFS analysis, but the way they are doing it is slightly different from what Yanis was showing us an hour ago. Yeah, but more details will be in the talk. Now, Jeff, good to go.
All right. Did you start recording?
Oh, the recording is running.
Oh, it's recording. All right, perfect. All right, so let me start by sharing my screen. Can everybody see the talk?
No, not yet.
Oh, not yet. Oh, that's not good. How about now? No. All right, let's try that again.
Yeah, it works now.
All right, there we go. How about that? Now can you see the talk? Yes? No? Maybe?
I do.
Okay, perfect. All right, so
Yep.
One minor correction, we're not using neural nets. So we're using a genetic algorithm to identify the species that are present in the XAS. So one of the big differences is a neural net requires you to have a large set of training data that you know perfectly. We rarely have that for some of the things that we're working on. And so it was very difficult for us to put together something that used a neural net. So we went back to an earlier concept that was first actually postulated and demonstrated, as far as I know, by Grant Bunker. And so I'll talk about that in a little bit. But basically, this project was funded by Idaho National Laboratory under their LDRD program. And we'd like to thank their former director now, Mark Peters, who was very supportive of this project. And Matt Newville from CARS at the Advanced Photon Source, because without Larch and LM-FIT, I don't think I would have even have attempted this project. So the work he did making Larch and LM-FIT, absolutely invaluable. And here we have a large number of people who have provided some data for us to analyze, and especially Carlos Segre and his former student Yujia Ding for the battery cycling work or data that we're going to show. All right, our collaborators on this project, Donna Guillen at INL, Andy Lau and Min Long at Boise State. We have a tremendous amount of students work on this project. Here at Illinois Tech, Chandler Sun did the majority of the early work on the genetic algorithm, and Shlomo Argamon also is a faculty member here at Illinois Tech from the computer science, who really helped, especially with different models of variance and understanding the meaning of the results. So one of the things that triggered us to start this work is the problem of reproducibility and replicability in science. And science is a very interesting thing, but it's somewhat problematic in that we see, varying things, take baby aspirin, don't take baby aspirin, don't bother. All this stuff changes as our understanding of science changes, and that's partly because of problems with reproducibility. Non-replicability can be a problem, bias in researchers, sloppiness, all these things can cause great problems. And one of the things that we can do to help prevent this is to go ahead and do something like utilize more artificial intelligence. Now, earlier this year, Linford et al., and I participated in this, we became concerned with faulty materials data analysis that was propagating through the literature. So I'm a journal editor at the Journal of Applied Surface Science, and it's gotten to the point where if I read through a paper and I see immediate flaws, and I think the science is interesting, I have a sheet that I just send back to the authors that says, you have some problem in one of these areas. If you really want us to consider it, you have to fix this before you can resubmit it, and we'll send it out for review. And that's problematic. And one of the reasons for this is because we're getting more submissions by, for example, synthesis experts who aren't characterization experts. And a lot of this is funding related. We don't train enough materials characterization experts anymore. We don't provide funding for them to work with synthesis people to do work. All these things are problematic, but they show up in the literature because interesting things get published and aren't caught in the review process. So with materials characterization, we typically want to extract information about a sample, and we want to create a physically meaningful understanding of the physics and chemistry that contributes to the experimental data. And in our curve fitting and modeling, our goal is not usually to create the best mathematical fit, but it's to create the best physically relevant fit. And so you have to consider the physics and chemistry of the system while you're trying to extract information from the experimental data. So I'm going to take a brief aside here to photoelectron spectroscopy, because there have been studies done that show the amount of poor data that's getting through. It's similar to XAFS. A photon comes in, but instead of looking at the absorbed photon, you're actually measuring the emitted electron. And you get peaks in the data that looks like this, peaks versus binding energy. And on real simple systems like carbon and oxygen, you can directly identify which component belongs to which carbon type in the material. Same thing with the different oxygen types. And this is very good. And you can extract this information with curve fitting if you do it well. The problem is with photoemission, there are other things that complicate the situation. There's spin-orbit coupling. There are Koster-Kronig transitions. You can have resonance. There's inelastic scattering. And all these things have to be accounted for when you're trying to extract the chemistry and physics from the system when you're doing the curve fitting. And so a recent study by Major et al., and this was just finally published last week, went through and they had a bunch of experts where they sent out papers every week. Journal would come in, they would go through, they would all look at the data, and they would identify problems in the spectra. And now I don't know anybody who's done this for EXAFS, but it's easier to do with photoemission because you can usually just look at the spectrum to see. So here we see the background in this peak, this peak, this peak, goes through the center of the data. It doesn't fit the background at all. So it's easy to tell here that there's a major problem. Another thing that they left out is they showed the raw data and they showed the two peak decompositions, but they didn't show the best fit to the data. So that's a problem. How can you tell if this is a good fit if you don't show the total fit? If you don't show residuals, if you don't, all these things are problematic. We can go through here. Here we have a calcium 2p and a nickel 2p that were fit. Now in this case, this is the calcium 2p 1/2 or 3/2. This is a calcium 2p 1/2 peak, and the background really goes like this and comes from here to here. Here, they assume that they could run the background up to here and just fit one component. And that's not allowed. You have to include the whole amount of physics. Same thing here in the nickel 2p. They fit with singlet spectra and don't have any idea about the spin orbit multiplet splitting that's involved in the system. And so on the image on the right shows how you would fit this with a true multiplet and include everything you need to do, including the relative shake-up, shake-off peaks. And so all these things have to be done. But the problem with XPS is it's found at almost every university. There's usually one expert running the instrument, and they can't work with everybody to actually analyze the data. Here we have a case where this group of researchers just showed the fit. They didn't show the raw data at all in this spectrum. So again, it's really easy to look at these things and identify them. Here they have a large range of full width at half maximum. We have a very narrow peak here, a very broad peak here. And that can happen on occasion, but when it does, you have to explain why. You have to explain the relevant physics. Here in sulfur, they have the wrong ratio of spin orbit splittings. They actually assign chemistry to spin orbit split peaks. This is clearly wrong. They also have a wide range of full width at half maximums of the peak. And you can identify this just by looking at it. You don't have to do a whole lot of work compared to EXAFS, where you would actually have to read into the data or to see, for example, if somebody had negative amplitudes for peaks. And that's why I don't know if anybody's really done this for EXAFS, because it would require a lot more work than just looking at the figures to tell the problem. Here they have the same peak represented by peaks at different binding energies. So we have peaks here, here, over here, and so who knows what's going on here. This is an example of a good fit, but it's a good mathematical fit, not a good physical fit. This is one of my favorites. This group basically labeled all the noise peaks. So they got a table of binding energies, and they went through and said, okay, that peak is whatever this is, even if these elements weren't present in their sample. So this is not good. And what's important to understand here is all of these are published spectra. All of these made it through peer review. That's a big problem. And so we were concerned about this and thought maybe we could bring artificial intelligence to bear on this. But the problem with photo emission is it has all these things that you have to add in additional intelligence in order to understand and to do this peak fitting. So we thought, what about XAFS? XAFS would be a good place to start because everything's based on relatively simple sine functions. It's well parameterized. It's well understood how to actually go through and utilize all these sine functions. And Larch does a great job calculating all of them. So as long as we have a model that we can work with, we can utilize Pfeff and Larch combined to create all the paths we need to use in our fitting of the data. So how we would really like to see this go forward as we keep using this, we would expect to have materials inputs that we can use for path calculations, calculate them using Pfeff, compare to experimental data off the beamline, put these together in our genetic algorithm with ArcProt and Larch, ultimately get the results out, and ideally feed this back into the materials project and to FEF9. There are interesting things that why do some paths show up in the data? Why are some paths more important than others? And we think there's some interesting physics there that we can look at. So XAFS, I'm sure we have people who typically understand XAFS here, but typically it's done at a storage ring where we take light at our beamline at the advanced photon source. It's typically off of an ID beamline and insertion device. We have a cryogenic silicon 111 monochromator. And then we have all kinds of methods for actually measuring the XAFS, whether it's transmission or fluorescence. Now, historically in the past, you needed access to a synchrotron to do XAFS, which is a little different than photoemission, which is still predominantly lab-based given the number of lab sources out there. However, the EasyXAFS changes that. We have an EasyXAFS system here at Illinois Tech now. And this is a relatively cheap system, much cheaper, for example, than photoemission systems, which are ultra-high vacuum and typically on the order of $1.5 million. So compared to that, I expect the EasyXAFS will start proliferating, and we'll see more and more lab-based data off of a number of systems. Sometimes you really don't need the intensity of a synchrotron, and you just need time. And so you can count in a lab for a long time with the EasyXAFS system. And so I expect we'll see more of a proliferation of bad XAFs as we go through in the future. So here we have a copper K-edge. This is the absorption from a 1s orbital. This is data taken at 10K. It's often used as training data at various X-ray workshops, XAFS workshops. Once you have the raw data, you extract the oscillatory part of the spectrum, and that's your chi function. And this is the data that we're going to work with in this talk. So what we're going to do is we're going to analyze this chi data, chi of k. So when we first started doing this, we took synthetic data. So we would just do calculations. We would pick specific paths. We would sum those together to get a spectrum. And then we would let our automated routine, our artificial intelligence routine, figure out what paths were involved in this raw data. This has no noise. There are no other complications. We knew what the values were exactly. And so we used this to test our genetic algorithm from the start. Now, when we think about one of the problems with XAFS, at Bruce Bunker's retirement seminar, he was a professor at Notre Dame. He talked about how he had trained 24 people over his career to analyze XAFS data. And one of the reasons for that is XAFS analysis does have a level of art to it. And so the idea was, could we get the computer to analyze XAFS data? And it turns out that applying genetic algorithms to XAFS data is an old idea, or at least a relatively old idea. As far as I know, Bunker, Demakis, and Kelashvili were the first to do it, and they used XAFs related to zinc metalloproteins. And so this work was done from about 2000 to 2006. And then obviously we saw Yanis Timoshenko earlier today with his both neural networks and reverse Monte Carlo with evolution. But for example, the analysis system that Bunker et al. Put together was never really put into large practice. And one of the reasons for this is it is slow. It is much faster to do conventional analysis with Larch or Athena, but now the availability of computational clusters and multiprocessor computers, we think, makes this much more practical. And so it's still not going to be a 2-second calculation, but it's over a reasonable time frame over which you can evaluate data. Now, we really start with human-assisted machine learning. So we have to provide the basic structure that we think is present. And this system works with mixtures. It works with well-defined systems. It works with systems that you don't necessarily have an understanding of in advance, as long as you can have some idea of what paths might be present. So, how does a genetic algorithm work? Well, it uses deterministic randomness. And so deterministic randomness, we start and initialize a random population. We evaluate the individual fitness, how close it is to the experimental data is what that means in this case. And then we select the best individuals, and then we basically mate them. So we cross them over to make offspring. We mutate people as they go along, and we eventually get a good representation over time of our experimental spectrum. So this does work very similar to genetics. It's an old system. I think genetic algorithms have been around since 1995. But basically, we treat our solutions as chromosomes. We have a cost function that determines the fitness. We mate where we cross over the best of each different group. And every now and then, we have to rely on mutation to change values randomly. So what goes into our algorithm? Well, the population size is important. How many breeders do you start with? The number of generations, how many times do you allow them to propagate? What the fitness score is, how many of the weakest members should be killed off? What percentage of the strongest members should be mated? How many children should they have? How many mutations should come? And finally, what's the ending criteria? How do you know when to finally stop the calculation? Well, for mutations, we use something called the Rechenberg algorithm, which dynamically alters the mutation rate depending on the number of successful mutations. So the number of mutations rates will change to try and get you out of a local minimum if you're trapped in one. So it allows you to explore a lot of phase space quickly. And for fitness, we used a reduced chi-squared, so we can compare models of different numbers of parameters. All right. Over time, we found that we had to add additional intelligence. And we knew we were going to have to do this ultimately for the photo emission, but it turns out it's important for the EXAFS as well. And so we can run with a single pass or a two-pass routine where we calculate the path contributions and we can remove or add paths depending on what we see finding. So when we first took a guess at what paths were going to be important in fitting the copper, it turns out we missed some. And just like in the earlier talk, it's very important in many cases to really understand what's happening here at these high values of R. And it turns out finding this was not easy, and our intuition about what was going to be important there wasn't very good, as we missed it entirely. One of the hardest things with this is determining errors. Error analysis, how good you are, your statistical error, it is probably the most challenging thing for fitting this data. We can get very good fits, but the question is, how good is it? What does it mean? And so we basically adapted the uncertainty quantifications of a genetic algorithm for neutron energy spectrum adjustment that came out of Sandia National Laboratory. And so one of the things we do is try to determine the statistical error of the genetic algorithm. And so what we do is we run the calculation multiple times. So when we're doing this, we typically run 100 calculations with various initial conditions. where we changed the number of populations, we changed the completion criteria, we changed the mutation rate, we changed the population size, we changed the number of parents, run the system through, and we've used this to see what the variance and what the final end state actually is. So like I said earlier, we started by using that simulated synthetic data where we just took known paths without noise. We used the genetic algorithm to reproduce those. And it turned out that worked very well. So we quickly ended up moving on to measured experimental spectrum where we looked at simple molecules, crystalline solids, and mixtures, including those of operando batteries. So here are three simple technetium compounds, TCCl62-, TCOCl4-, and TCNCl4-. We have octahedral and square pyramidal shapes. And so what we did was we ran our algorithm on this based on the known structure in the FEF input files. It converged, it matched up with what we get for human analysis. We can see some peaks are probably less important than others. This is clearly dominated by the technetium chlorine path. And the second scattering path, probably not too important, maybe not the third. So we can get an idea of what's really important in this data set by looking at all the paths as they contribute. We get a nice idea of what components are there. So we decided early on, because in XAFS you determine S0 squared n, that we were going to leave n fixed at whatever was in the FEF calculation, and just instead of adding another parameter to vary x that was x times n S0 squared, we just vary S0 squared. Because most of the time we have no idea what S0 squared is when we're actually working. But we get values that make sense, bond distance 2.34, etc. And we see the paths, TCCL is the dominant path. Like I said, the second and third paths maybe not too strong. Then we see more paths out in path 3 and 4, more strength in those paths. So these are the important things that contribute to this data and reproducing the spectrum. For TCOCl4, we can do the same thing. We get very good fits to the data. Again, we see paths that are important. We can see the TCO. And again, the spectrum is still dominated by the TCCL bond distance, which we would expect being as it's the higher Z material. And we get, again, reasonable values. And we can extract the Debye-Waller information, the bond distances, etc. Same thing for TCNCl4. The nitrogen was a little bit weaker here. But again, we see the dominance of the nitrogen and the chlorine paths in the data, and the multiple scattering paths are fairly weak. And so the only input to this data was our FEF structure file that we used to calculate the paths, and then we run the system based on those FEF paths for the known compound. In terms of crystalline solids, we've done things like hafnium oxide, copper, hematite. We've run through a lot of systems. We find what paths are important and what goes into making up the data. So for copper, FCC metal, copper-copper, bond distance about 2.55 angstroms with 12 neighbors, 3.616 neighbors. And we can go ahead and fit all of this data as well. So this data we can extract at different temperatures because those data sets exist. So we can fit at 10K. And we tend to, when we're fitting a series of data, utilize the data set with the most structure in it. So we use that to identify which paths contribute. Here we found that 1, 2, 5, 10, 16, 28, 29, 30, 31, 36, 37, 40, 41, 42 were the important. And these had bond distances of 2.53, 3.58, 4.42, 5.14, I should say R distances. And we go through and see what's important. And we do tend to see eventually a fall off at high. So we're at 0.9s early on. And some paths don't contribute that much, other paths do. But these are what makes up this data set. So we use the data with the most structure to determine which paths are important, and then we carry those over to the higher temperatures. And we repeat the fits over and over with those same set of paths where we find out which paths are relevant. So here's the 50K data. Here is the 150K data, 298K data, and you can see the Debye-Waller factor is clearly changing as we go through this, but that is the dominant thing that's actually changing in this data. So what we can do is then we can plot the Debye-Waller factor versus temperature for the single scattering paths with the error bars, and we can see at low temperature in the first two paths, there's not much change, but then it increases rapidly with temperature. And that's fairly common, and there's not much difference between the 10 and 50K, but then we get an increase as we go forward. What's nice about this is our data does make sense in many cases where we have strong paths. There's lower uncertainty than in the weaker paths. So clearly, if a path goes to 0, the uncertainty in all the other parameters are sigma has to be infinite. So if that path goes away, the uncertainty has to go large in the other paths and the other components of the path, because they can be anything. So it's good that we see that correlation with weaker paths having higher uncertainty than lower paths. All right. One of the first blind tests we did was with lithium-ion batteries. And tin is a potential replacement of cobalt in batteries. So we took EXAFS spectra while charging and discharging the battery, or as the battery people here prefer us to say, while lithiating and delithiating the anode. And it turns out that when they're running these operando battery systems, they just can't analyze all the data individually. And so this was a test of our machine learning code to see what we could pull out of this. So during the actual experiment, they measured the tin K-edge XAS versus the battery state of charge or the amount of lithiation. Now, what we didn't know in advance was that when they did the analysis, they summed all the like cycles to improve the signal to noise and what they analyzed. So they took, for example, all the lithiated peaks, summed them all together to improve the signal to noise, and summed all the delithiated cycles or spectrum, and then analyzed those. And they didn't analyze the transient at the start. And when they did this, they identified important paths as being tin oxide, tin lithium, and tin tin. And so they gave us this information about the data and gave us the data. Now, what we ended up doing, because we didn't know that they had summed all the data together to analyze, was we summed 10 consecutive spectra to improve the signal to noise ratio. We also analyzed the transient decay cycle, and we picked the human important paths. But we actually found out that there were 2 additional paths that were also important. A tin sulfur path, because this material actually started out as tin sulfide. And then we also had another tin lithium path that turned out to be important. So it was a blind test. We had no idea when the battery was cycled, And what was nice is we were able to clearly observe the cycles of the battery as it went. So here we have a bunch of different paths. We have tin sulfur, tin tin, tin oxygen, another tin tin at 2.85 angstroms, a tin lithium at 3.1, and a tin lithium at 2.67. So as we did this, we quickly see that the tin sulfide is completely destroyed. So it starts off with some fraction and falls off over time. This is one of the parasitic reactions that occurs in batteries with tin lithium. The tin lithium, or the tin sulfide that starts off as the anode material, gets totally destroyed as the battery operates. The tin oxide, the oxygen is only present as an impurity from preparation in air, so it gets driven off as well fairly quickly. This short tin-tin bond at 2.85 angstroms tends to go away. Or sorry, at 3. No, that's tin oxygen. This is tin oxygen. This is the tin-tin bond at 3.7. It goes away. Tin oxygen goes away. And we're left with 3 paths that really cycle as the battery is operated. And so we have a 2.85 angstrom tin-tin path that we can clearly see cycling. We have a 3.10 that beats in opposition to this. And so this is what happens as the battery is lithiated and delithiated. As it is lithiated, it breaks the tin-tin nanoparticles up and the lithium gets incorporated into the tin, and we can see that clearly happen. And then we have an interesting transient species, which is a short bond distance tin lithium. And you can see it kind of looks like it's decaying away over time. It would have been interesting to see if this peak would have totally gone away after maybe 10 or 20 cycles. But we could see these main reactions here and a couple of parasitic reactions that occurred in the data. And so this was all great. I was very happy with this because we had no idea when they were cycling the battery, but the algorithm was clearly able to identify this and the different mixtures and species that were present. But the grad students showed me the raw spectrum. This is horrible data. Had I actually seen this, I would have told them never waste your time with this because you have no chance of pulling anything out of that. But the fact is, we were able to pull things out of that. Now, this is one of the worst of the generations in the data, but we were able to see things that actually made sense. So if we look now at some of the better data as we go through, this is the as loaded, which had all the transient species. We were able to see this, but it was clear when we ran the algorithm that there was a species missing. And so we had to add this tin sulfur path in order to basically understand the initial transient operation of the battery. As we go forward in what we're calling the discharge state, this was the worst state that had the absolute worst EXAFS, and we can see that path 1 tin lithium bond is nearly gone here. The path 2 tin lithium bond is here. These were the worst data, and obviously our algorithm said this had the worst statistics. And so our error bars on this cycle are worse than any of the others. And then as we start rebuilding the nanoparticles where the tin-tin path comes back very strong, and we get a tin lithium path transient, that's that short bond distance lithium peak. The data is much better quality, still not great, but what's interesting to me is we were still able to pull trends out of this data. And to be 100% honest, I wouldn't have thought that possible had I looked at this data in advance. I would have said this was not worth looking at. But fortunately, we didn't look at this first. But we were really able to see and identify the cycling. And so even with the horribly noisy data, we could still extract the trends. And I don't know, to be 100% honest, if humans could have pulled all that out, because I think if it were me and I saw that data, I would have summed all the cycles too, just as the human researchers did. Now, it's also important to be able to show, because here you're summing sine functions, that you can't reproduce anything with your sine functions. So this was a fission triso fuel that had uranium in the barrier layer, which is silicon carbide. And so one of the things that people wanted us to show in the analysis of this data is what wasn't present. And so some people thought that UO2, which is the fuel, had diffused throughout the triso fuel particle and got stuck in the barrier layer. But when we try to fit with UO2, it's clear we couldn't reproduce the data. And if you look at this, based on our pass, it's clear that this is an unphysical fit, because here we have the second multiple scattering path being very strong, but the uranium-oxygen bonds that this path depends on not being present. So we were able to quickly exclude different models using this just by running these structures. So we can include a lot of different types of structures when we go through. Not going to show what this actually was a fit through, but it's actually a uranium silicide compound predominantly. And so the uranium breaks up the silicon carbide layer and forms a silicide. There's a little bit of carbide, so it's a little bit of a mix. But, you know, what was nice is we can also do things that the reviewers wanted. Can you exclude things rather than how we typically work in XAFS, where we fit and show what's actually present? So with our model and our software, we're able to exclude different structures as well. All right, so what we do is we effectively fit EXAFS data using a set of FEF9 calculated theoretical standards by using a genetic algorithm. And this works on both high-performance computers and on the desktop. And I'm not going to lie, we normally run this on the clusters, because the job control software on a high-performance computer is really, really convenient. We're trying to duplicate this job control in Python. We haven't been able to successfully do that yet. But all of our code is written in Python. It is it's open source. I'll take you to the repository in a little bit. But the time it takes to develop a reasonable fit is a fraction of a day on a desktop machine. And it depends on how many paths are important in your system, but we usually let it go and then come back when it's done. All right, but to get back to photo emission, we've also worked on photo emission, because the basic underlying fitting routines and the genetic algorithm don't really care what the shape of the functions you're trying to fit are. And to do this, we're still utilizing Larch and LMFit. We forked it because we didn't want to risk destroying all of Matt Newville's work, and we'll merge everything in later. But we're adding functions to LMFit for XPS. And realistically, we should be able to apply about 80% of the XAFS algorithm to XPS fitting. One of the hardest things we had to do was get some of the background of the inelastic scattering functions put into the data. So we've done that. And this is our first XPS fit using the exact same algorithm. So we've been able to successfully fit carbon 1s spectrum so far We still have a number of functions that we had to LM-fit to really do XPS well, but we're going to be continuing this work in parallel as we continue to develop all of the algorithms based in this work. But again, looking at it, we'll be able to apply about 80% of the EXAFS algorithm to XPS. What's going to be different is all of the different optimization tools and all the optimization intelligence. So the path optimization isn't going to be as relevant to XPS as it is to XAFS. Some of the other XPS intelligence that we're going to have to add won't be as relevant to XAFS. But we'll be able to reutilize a lot of this code, and that means we only have to develop and test one basic genetic algorithm code base for everything. This should be just as applicable to diffraction fitting as well. So we think there's a lot of potential benefits to using this. And so it appears to us that AI techniques certainly have the potential to lighten the burden on human analysts. Does that mean we can reduce or remove the human? Not 100%. You still need judgment. You still have to look at all the data. There are use cases where different systems are going to be better than others. There are a number of cases where using reverse Monte Carlo is going to be better. There are cases where this is going to work just as well and be faster. All those things are important, and there are a lot of different things to do. And so I think all this stuff is actually very complementary. Right now, the human has to enter what paths are present in the material, and you have to give it a number of systems if you're going to evaluate multiple species. What we would like to see going forward is that a neural net can identify the likely species to form. So if I have sulfur, oxygen, and tin in my material, ideally a neural net could go out, search the literature, figure out that tin oxide, tin sulfide are the most common things that would be present, and then you can use that to launch your PHEF calculations based on those structures. Have PHEF9 calculate the potential paths, and then let the genetic algorithm determine the prominent paths that are there. And then ideally, if you had a nice database of structures, you could then use, based on what paths are present, the neural net to identify structures from the past. Right now, that's all done by humans. But I think in the future, that's an avenue that we will definitely explore. So with that, I want to go ahead and start trying to demonstrate our software. This is the first time it's available. We highly recommend that you use Anaconda as the environment, but the project is called EXAFS Neo Public, and it's available on GitHub. So with that, we'll go on to demo and training, or if anybody has any questions, I'll be happy to take them. I probably should have just killed the routine rather than that, but that's... All right, any questions?
Can I ask a question using my...
Sure.
Right, so the talk speaker. So in your example about copper, I noticed so some of these passes have this SO2 factor like 0.1 or 0.2 or something. So what's the physical meaning of that? Because I assume it's a spectrum was for bulk copper foil. So all these SO2 factors should be equal to 1 or something that is close to 1, right? If this pass is identified correctly.
Yeah, so for most of the paths, the very strong dominant paths, it's very close to 1. Yes. So if we were, let me see if I can still pull this up. Hang on. Copper. Oh. Like here, for example. So, these early paths, this is all very close to 1 for the strong first 3 copper paths. Now, as we go farther and farther out, where we start getting multiple paths at the same distance, this changes and these values drop. 0.4, 0.3. So this is telling us that that is not a path that is showing up as strongly in the calculation as one would expect. That is an interesting result. Obviously, we see others out here that do show up fairly strongly. And so this is an interesting question as to why some paths are calculated to be stronger than they're not. And so we're actually working with the FEF team to try and figure out what some of this means when we see these. A lot of the single scattering paths aren't as strong as we thought that they would be as we go through and see this. So we do think there's some interesting physics going on here, and we don't always know exactly what it is at the start. But clearly these paths don't play as important a role in reproducing the data.
So maybe I have a follow-up question / comment, because one of the reasons why we really pushed forward these reverse Monte Carlo simulations was that it is known that some of these multiple scattering passes, they are very sensitive to the angles, or bonding angles, especially in all these cubic materials like copper, for example.
Yep.
And it seems to be that in your case, you don't really take that into account. So maybe that there's some small changes in angles in the material kind of kill significantly the importance of some multiple scattering passes, and that's why they don't really hear it.
Yeah, I would not be surprised. One of the things that we see, not so much in bulk material like this, but in thin films, we have seen paths disappear that are almost certainly because of the polarization vector of the light. And so we see both the direct paths and the multiple scattering paths based on those will disappear. And a lot of people don't take that into account when they're doing the fitting, for example. This has actually told us that some of the films that we're growing are actually much more epitaxial than we thought they were. And so I think there's a lot of things like this that are all very interesting and very important. Yeah, so it really depends a little bit on what you're trying to extract from the data. But yeah, these are all interesting things that I don't think people always see when they're just fitting the first 2 or 3 paths and fitting over a small distance in R space. And I think there are a lot of interesting things like this that people miss. So, for example, we haven't done a lot of work on reverse Monte Carlo, but we've done it the opposite way, where we've done Monte Carlo to try and simulate radiation damage and then try and calculate the FEF spectrum. And so things like that, or calculate the true absorption data. So these are interesting things that do often get overlooked. And so I think reverse Monte Carlo is a very good way to get at many of these things. I think doing Monte Carlo calculations are also a good way to get at some of these things. But part of the problem is I'm not sure how many people are actually fully qualified to do things like that. It's always one of the dangers. And so I think at some level it is important to try and make the technique open to as many people as possible. And so I think that's a good thing. I think it's good to see exactly how everybody is pushing all these new machine learning techniques forward. Any other questions?
So we had a couple of questions, but I believe your demonstration will answer.
Yeah, so basically, we don't code in Larch, but we use the Larch plugins in Python. Everything is available on the GitHub page. So let me start sharing my screen again. To hide keynotes. So we start with Anaconda. We highly recommend everybody install Anaconda. I am not going to install Anaconda here, even though it is fast. I already have it installed. But if you want to, you can certainly install Anaconda. I think it's a great development environment for things like this. Oh, did I just kill? So if I go to our GitHub page, everything is here. There are example files for copper, technetium, and uranium in here that you can use to try and reproduce our calculations. The instructions are kind of sparse at the moment. We're trying to get people to use this and give us feedback. So we would love to have as many of you download this and use it as possible. And so I'm going to come back here, open up a new shell, and I will basically install this from scratch, but I'm going to look to make sure CLS XAFS, that I call it the right thing, so all my further so basically, I'm going to create a new Anaconda environment. I'm going to call it CLS XAFS, and it has to use Python 3.7, NumPy, Matplotlib, and PyQt. So it'll go ahead and ask me to proceed. I'll go ahead and do that. Fortunately, none of this takes too long, I hope. All right, so now I have to activate my environment, CLS XAFS. And now I have to install Larch. All right. Now I have to clone our repository. And you know what? I think I have this copy and pastable down here, so I'm not going to risk typing it in wrong. All right. So there it is. So now I have to change into that directory. There's everything I need. And so now I just have to do Python. All right. Now, from here, we could run everything from the command line. But we also have a GUI. And to run the GUI, we got to change into the GUI directory. And our program is exafs_GUI.py. So we run that by typing Python 3, exafs_GUI.py. And if the stars align, oh, awesome. I hate when that happens. It dies. No module name PS utilities. Interesting. That's a new one. All right. I know Andy Lau's in on this. So Andy, we got a new bug. So we should fix that. Don't know what's causing that. Fortunately, though,
You could try conda install psutil. This may solve the problem.
that could work. But I also have a working version because I'm not completely dumb enough to try this without conda install psutil. Oh. Oh, interesting. All right, let's try that again. Nope, no module name Larch. That's not good. Oh, I know what I did. I bet I didn't install Larch in this. I may not have installed. Let me reinstall Larch. I may not have activated this environment before installing large. And install, see. Let's try that one more time. That's odd. Okay. So otherwise, I'll just switch back to the old one. Okay. Gonna read Python 3. Right. Let's see. Oh, there we go. I must have installed Larch in the wrong environment. All right, so there we have our GUI. We come up with the inputs box, populations. These populations you can play around with, but we find this is a good batch that works for most things. 1,100 generations, 20% best individuals, 20% local survivors. This is where we select the paths that we're going to look at, the mutation chance, the original chance of mutation. Again, these are parameters that are a good baseline. These are the parameter data sets that we would want to use, and this will depend on every individual XAFS spectrum. I need to drag the window open a little bit because I like things being bigger. Output, this is actually information related to our input files that were generated. So we can run the code from this GUI, but we typically also use it to generate a lot of input files. And then here's where we do the final analysis. So let's come back to the input. So I'm going to choose a file. CLS demo, and so I'm going to take technetium CL6. I'm going to choose an output file here, and we'll put it in the technetium directory, and I'll call this live, and we'll make this tccl6.csv. And now I've already created a folder for technetium with the FEF files. So if I come back over here into JFEF, I can open the FEF input file and I can view it. And we see the technetium atom surrounded by the octahedral chlorine. So that is exactly as we would expect. We would do save and run if we were going to run the calculation, but we've already done that, so there's no need. So that's the first step, is to create the FEF files. So these are all in the TCCL6 FEF file. Now, I'm not going to run through an entire path optimization because it would take too long. So I already know the most important paths here are paths 1, 4, and 7. And this data, just to be clear, TCL6, best came in 4 to 10. I can come here, plot background in mu, plot the data in K-space. It's nice because clearly Larch is working, and then in R space. Okay, so populations all look good, mutations, Larch, background plots. So I always look just to make sure everything looks reasonable before I start the calculation. Some of my students have much more trust in how everything works, and will just go ahead and start. but we hit run, and the data should now be running. So with this small number of paths and this small molecule, it's taking about 3.6 seconds per generation. So we can watch the data come by. And as you stare at this long enough, we name this software Neo because all the flying text boxes make it look to us like the text in the Matrix. So that's how we came up with Neo for the name. But this is going to run for 100 times, and we can see the history best reduced chi-squared and the history best chi-squared decreasing as we go. One of the most difficult things for us to determine is actually the offset in E naught between the calculation and the experiment. That is a very difficult thing to do. Obviously, doing the background subtraction is also a complicated thing. And so one of the things we strongly recommend is people try a number of different background subtractions. And then watch how things change as a function of the background parameters. Backgrounds are still one of the most complicated things in XAFS analysis. I can't tell you the number of times where I've looked at case-based data, talked to the students and said, that's not right. Why isn't it right? I don't know. It just doesn't look like XAFS data to me. And so that is one of the most difficult things, in my opinion, to still do with XAFS, and is still challenging.
That's a nice application for artificial intelligence.
It's a nice application for something. I don't know what it's a nice application for, but in my opinion, it really is one of the most difficult and challenging things, explaining somebody when their background's bad. Because their data just doesn't look good. So how we do this? Oh, go ahead. What's the question?
We had a question if there's a reason to use JFEF and not this FEF Lite included with large.
So the reason I use JFEF is because I do like to be able to see the input file. It's usually very clear if you've screwed up in the input file when you look at it. Again, if you're doing single scattering path analysis only, it's not that critical. But if you're doing multiple scattering, say you have an alloy, you want to make sure, for example, that your alloy compositions are uniformly included throughout the entire FEF model and not just localized on one side, because then you don't have an alloy, for example. And so things like this, I think, are very important. That's why I like looking at the FEF input file, just to make sure that it looks reasonable. But you could use the free version just as well. It would be fine. But then I think you should look at the data with some other program just to visualize your structure and make sure it's really the structure you think it is. So as the routine is going, it's for the first half of however many generations, it is randomly adjusting E naught, trying to search space in random. After halfway, we actually do a localization fit of E naught to determine the best value based on the parameters we have, and then it fixes that going forward and tries to modify that going on. And it does that routine one more time at the end as well. But E naught is really hard because all the paths have the same value of E naught, so it's not easily breedable. Fortunately, it also doesn't have that large of effect on everything. So
there's another question: if there's a PIP installer, PIP for your package.
Not yet. We expect there will be one. So we typically go with this route, just pulling it off the GitHub. But we'll build an installer.
Mm-hmm. So the code looks pretty fresh.
We've been working on this over the last maybe 3 years. So it all started out with a number of undergrads working on it. And then we have Andy from Boise State who came on about a year ago. Andy's a PhD student at Boise State. Great addition to the team because he has added a lot. So he's a computer science major at Boise State and has really removed some of the physicists from the code and turned it into a little bit more computer science rational code, which I think is a good thing because physicists tend to write code that works and not always the cleanest. And so Andy has done a lot. The code is much faster now that Andy's gone through it. So this has been a good thing. All right, so now we're complete. We have our final fitness score. And again, we normally wouldn't run that. And so now I go to with this few number of pass. So that's kind of an artificial example. But we come in here for technetium, and this is the analysis is in the live folder. We choose that, and then we can run the analysis, and we get this output here. We can plot the data in K&R space. We get that there. And since we mentioned earlier that we really want to do this to make it easier for people to display and show the data, we output a lot of the information as a LaTeX table, for example. And so then we can go into Overleaf, paste that in there, compile it, and we get a nice table with the various parameters. And now, some of these parameters are abnormally small because we've only run at runtime. Again, normally we would run this at a minimum 10 times to get better statistics on the error. But we think this is a very reasonable thing. In fact, most of the time we run this 100 times with different parameters set to build up better statistics. I probably should have changed that to TCCL. Sign _ 6. 2 minus. Recompile it so I know what it is. But we tend to have things that just do that and make it easier to actually display the output. The other thing we do is we like to make publication quality graphs in Igor Pro. So we have it set up so we can make a plot very quickly. So we load in the text. So that's in live again. And you get these outputs. I like to show all the paths, so that's in the individual fit. So we can open that up, load all this in. And then open up a procedure file that's not exactly a procedure file, but if we copy and paste this, put it in the command window, we get our plots. So we have a plot and an output table that we can use very quickly for publications. So we've tried to make this as easy on the user as possible. We expect over time that people who like GNU plot will make similar routines for GNU plot since this is open source. So we have that, and that's the analysis for TCCL6 with not all the paths, but it does a pretty good job with just 3 of the paths because those are the dominant 3 paths. So I have other examples to go through. We can go through the Copper 298 and show other ways of actually using the codes. If I come back here, I can start killing some of these things and switching from technetium to copper. So the copper data is 298K. We'll run that there. So
Wondering
CLS.
if there's a scripting way to automate this. So instead of GUI, if you have multiple projects and you just want to run it once. And
Yes, and so the GUI is a very recent, and I don't know if everybody saw what popped up, but all the students made me include a warning on the GUI that the GUI is under horrible development. And it is, they actually added the nice beta tag to the GUI. So let me actually come here. And so the GUI at the moment, really what it does is, let me find an example of one of these. Creates these input files. So yes, this is eminently scriptable if you want. Oh, that's not, I overwrote the input file. Oh, that was not smart. I do that every now and then. So yeah, we oddly enough, and I especially am a command line person, so I work from the command line. But there's a fairly simple input file format. I'll show you one of those right now because we're going to make them. But let me show you that. So as we go through here, let me go back to copper. And we will call this live to folder live. We'll call this output CSV. All right, populations are good. Paths, for this one, we want to use a different set of paths. So I'm going to pull this down here and copy and paste it from here. So we know what paths we've actually optimized for, so I'm not going to do the optimization. If I wanted to do an optimization, I would click the path optimize button, but we're not going to do that because we already know this. But so path optimize runs the routine twice, so it takes twice as long. Well, not quite twice as long, but you start with a larger amount of paths typically, and then it will remove some of the paths from the second go round that it determines are not relevant. So 2.5, 13, 2. So if I do this, I should be able to plot the background in mu. That's clearly copper, K-space data, R-space data. All right. So if I come here and we're going to do this kind of normally how we would create multiple input files. I'm not going to create 100 input files right now. I'm going to make 10. And so I personally don't use populations as low as 100. I usually go 1,000 to 5,000. I typically don't go up to 500 generations. So 150 and 75 generations are what I like to do. But the wider you probe, the more results you get. So if you go over too long, and then perturbations 20 to 50 is usually pretty good. And so then I can hit generate input files here. It'll ask me where I want to save them. And I created a live. So I have a new folder here. I'll call that inputs and choose. So now if I come in here, live input, now I have input files that I haven't managed to overwrite yet. And so yes, this is very scriptable. You can change all these based on whatever you want. Easy enough to just change all the different FF files in this all it's related there. So you don't have to use the GUI. It's easy to create scripts to do this and do these changes. We put the GUI together because I think people like GUIs. I'm old enough to not like GUIs, and I'm really old enough to not like programming GUIs at all. It's a nightmare. There are some weird things in the GUI that drive me kind of crazy, but we do have things like this. And so, yeah, it's just a matter of modifying this input file, and you can easily modify that. We don't like GUIs too. Yay, team. Good job. I wish I saw who had actually put that in there, but yeah, no, GUIs. So I can tell you the thing about the GUI that drives me absolutely most insane is changing the path range. So if you change the path range, it will automatically put in a 0 value. And so then you always have to delete this 0. And that's to make sure that you can't launch the code without any valid path input thing. But I would think there's got to be a better way of doing it than that. But all right, so now we have the output. So I have those output files. And so they're all right here. Perfect. We have them right where we want them. So now I need to come here. And if I'm going to run this like this, we're going to show you, and this is also scriptable, but I don't have a script for this yet. Because now we normally just pass all this data off onto the cluster and let it run. But I have 10 input file, 10 input files. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. I've got 10 windows. And then this is my favorite part because I can make my computer take off. So I have to do conda activate CLS XAFS. Can't remember if I put the E in or not. Woohoo, good. So I come here, do that in all my windows. And again, this should be scriptable, but this is parallelization on the cheap. And then I have to change to my one directory, and I changed that a little bit. So I think I put that in live. Inputs. All right, so there I have my nice input files all ready to go. And just to make this easier on myself, I'm going to copy and paste that. And now to run it from the command line, we go XAFS-I file underscore 000.I. And it helps if I spell XAFS right. And there it goes, running to its heart content. And I could do the same thing with all 10 input files here. So cd there, XAFS-I file 001.I, and it'll go again, this should be scripted because script spells better than I do. I'm not going to run all of them, but this gives you an idea of how you would go about doing it. So you start them. Clearly, this is taking longer because there are many more paths involved here than the simple technetium case. but I'll let it go through 1 or 2 generations. Yeah, I'm kind of surprised. Usually by now my laptop has its fans spun all the way up. So there's one that's moved on. So 59 seconds for that one because it has different. So this is population of 3,500. This one took 84 seconds. It has a population of 5,000. So we even here have a wide range of populations, 4,500 to go through. So they all take different amounts of times based on the number of passes, the number of generations, the number of survivors, the number of individuals. And that gives you a little bit more of face space to search. And so we think it's important. I strongly don't recommend relying on a single run of the data. At a minimum, I would do 10. I like to have 100. So I think that's something to keep in mind. Now, that is a number that we really haven't explored well yet, whether you need 100, whether 50 is enough, whether 25. And so we would hope that people will give us feedback as they use the code and run this. So I'm going to go ahead and cancel these things because we don't really need them, because that would take a long time to go through. But you want to create enough windows. And on my Mac Pro, I can easily run 10 at a time without any slowdown. It does make my laptop want to take off. But so I have my pass in here. I have the input data. The output file doesn't matter so much for the full analysis. Turn off create multiple input files. And so now I can choose where we're going to do this like a cooking show. So I already baked it last night, so we can pull up the results that we have from the copper from yesterday. So those were the multiple input files, but I don't want that, so I want here. And then I can run the analysis, and I get the same information in the table, plot the data in K&R space. I get a good fit to the data. Clearly, we could almost certainly benefit from including a little bit more pass out here at higher R, but and then this is a pretty good fit for 10. And again, the same thing happens here. We can pull the data. This is also saved as a data file, but if you're staring here, it's easy enough to look at this, pull it out. And then we can put this table in, and that would be copper metal. And we have a nice data file again with the pass described, with all the fitting parameters, all the error bars put in. And we can do the same thing here where we come back to Igor Pro. I'll do a new experiment. Don't need to save this. And load all our waves in.
I've just noticed that it would be pretty natural to use matplotlib if you are working with Python.
One could, but I've been using Igor Pro to make publications quality graphs for 30 years, and I'm not inclined to change. So yes, you could easily use Matplotlib. Andy's there. Andy makes a lot of beautiful plots using Matplotlib. Other people like GNU Plot. So I expect people will extend this for whatever they really like to put in. But I like Igor Pro because I can save the experiment and so, okay. open this real quick. So open up the procedure file. But yes, I imagine one could easily do this, matplotlib. Pull this out here, but you know what I like, I can do other things in here, and then I can save the experiment. Okay, re-encoded the text. And so if I just do new experiment, and I can also open an old experiment, and then everything returns for me. So I like Igor Pro. I've used it for decades, so that's why sometimes it's good to be in charge, you know. But I can go ahead and close this. Create a new experiment. So we tried to make it so it's easy to get publication quality figures out of this, how it's very easy to demonstrate, get tables that you can use. Even if you don't use LaTeX, you can then save this as a PDF file and import the table into your favorite document software of choice. Okay, another example. How we doing on time? We're doing okay for time. Okay, so that's it. UO2 nanoclusters. So the technetium data, the copper data, and this uranium data is all on the GitHub site. So people can go ahead and play around with it. FF data. To dump this back into live. Okay, populations pass. I have a different pass set for the UO2 nanoclusters. And for some reason that looks like the same, so it's not good. So let me come back here. UO2 data. And look at the log file to see which pass were there. Oh, 1 through 11. Okay, there we go. So now you get to see when I get rid of path range and try to type things. See, it adds a 0 every time, which is, as far as I'm concerned, the most annoying bug out of GUI protection that I've ever seen in my life. But it does prevent you from accidentally running it without any paths. All right, so the large range here is 2.5 to 10.5 or 10. RBKG background K labels 2. So we can come back here, plot the background. And that is the uranium L3 edge, data in K space and R space. And we've got it back to doing a single state file, large mutation. So I could hit run and it would start running just again as we did before. So you can run it one time from the GUI or multiple times from the command line. Again, I kind of prefer the command line. So I'm not going to run it because there's no real good reason to it. I'm just going to load the put together data, run the analysis, got the output, plot the K and R space data. So again, it reproduces the UO2 nanocrystallite structure very well. This certainly does take longer. We have to have the FEF files for UO2, but we think it does a pretty respectable job and gives output that certainly matches fairly well with your typical human analysis of the data. So I'm going to skip the hematite, and we were given an example of pyrochlorofluorite to pyrochlor transition by the CLS to look at. And so let me pull that in. And so that is this one here. And so where is the data? This data is probably in here. There it is. And so this is a sample that was heated to 1400 C. The FEF data for this is, let's see, probably in here. Okay. This was path optimized. Right. And the range on this data was 2.5 to 10. EKG weight. So let's look at this. All right, so this is the praseodymium edge, K-space data, and the R-space transform. Let's see. Oh no, I got the background K-weight wrong. So this is an example of how you have to mess with the background. This was our best background representation compared to that of the published spectrum on this. Was using our BKG as 1.2. This data was put together before Larch existed and was analyzed with some other software. And so this is one of the hardest things to do, in my opinion, with XAFS analysis, is match backgrounds from the different background analysis tools or background subtraction tools. That's that. And so that we have our best optimized fit to the pyrochlor structure. If you look carefully, it looks like we're still missing a little bit here. And the data actually, our GA reproduces the published spectra really well. And so it could be that this is a little bit of an offset due to the background, or it could be there's another small oxygen peak that's missing a little bit in the data. So from this, it's a little unclear. We've started now going ahead and mapping out mixtures of fluorite and the pyrochlor structure over the full data range of data space, but we didn't get that finished in time to go on through here. But I hope I've demonstrated how our software works and what you can do with it. And we hope people will download it and start sharing some feedback with us. So with that, I'll be happy to take any questions that anybody has.
I just can't comment on this latest example with pyrochlor. It's the real data that we published 10 years ago, and everything was analyzed manually, and it was a huge effort to go through all our scans. There was maybe more than 100 in total, and that was a lot of work for us and for the students who analyze this. So I think if we had such a tool to automate this all? Obviously, we would have to review the background subtraction, for instance. Yeah. So far, there's still some space for improvement. But in general,
now I didn't show it here, but you can subtract backgrounds. You can do self-absorption correction in other software and save the K versus chi data and load K versus chi data here directly. So you don't have to do the background subtraction with auto BK, which is what Larch uses. And you can do further processing and refinement. We're going to add self-absorption corrections into the code because we think that's important. And the other reason is we do a lot of fluorescence data on alloys and things like that where you have to perform self-absorption corrections. So that's why this release is 0.93 instead of 1.0, because there's still a few things that we have to add. But so you can load in K versus chi data that has been processed in other software, so with different background removals. But one of the things that I'm really looking forward as we keep going forward is to explore the effect of background removal. So changing the parameters up a little bit and see how that affects the fit. I mean, usually it's not going to affect the higher R peaks, but usually it has a significant effect on the lower R peaks in my experience. So I think those are all interesting things that we can look at going forward. Another thing I'd like to do, just kind of out of interest, is analyze the same sample collected on different beam lines and look at the different results. I think that would be a very valuable thing to do as well. So one of the things about Illinois Tech is we run one of the few XAFS databases. And so we host all of Farrell Lytle's old XAFS data. And so if people want to provide data to us where after they've analyzed their data, published it, let us know which paths are important, we can start then using that to try and populate a neural network to help pull which paths are important for structures going forward so other people don't have to do the same path optimization routines and things like that. They have a similar. So we would be happy to host that if people want to contribute that going forward.
Do you have a link somewhere? Maybe.
Let's see if I can find it real quick. Lytle XAFS data. IIT. Yeah, there we go. The XAFS database. So it's not a secure link, but it's ixs.iit.edu/database.
So Matt Newville during his talk mentioned that he is working or would be glad to see this sort of database, and this sort of discussions started very long ago, and I didn't see any to really grow to something big and useful.
No, as far as I'm concerned, right now there aren't any big and useful ones, and that's part of the problem. That's a huge problem if people want to use neural networks going forward because there just aren't enough experimental data. You have to rely on theory, and so yes, it's a big problem for things like that. So the ones I know of, there's one in Japan, there's the one at Illinois Tech, there's a small one at CARS that Matt runs, and there's one at the CLS that the VUV people have. So those are the only large databases that I know of. But it's something that's really needed.
I was wondering if there are lots of intersections in these databases, and if it would make any sense to merge them together
Oh, it would absolutely make sense to merge them together. The problem with merging them together, I think, is that ultimately it costs money, and somebody needs to fund hosting the repository for a long time. So my own personal take is it should be one of the synchrotrons because it's easier for one of the synchrotrons to be around for a long time. But the cars isn't uh, is a cat, right? It's run by the University of Chicago, which isn't really part of the APS. So I don't expect the APS or SSRL to do it, which I would argue are the people. Maybe CLS would do it. But yes, we do need a large database, a large repository with the ability to store all this metadata and all these parameters. And I think that would be very helpful going forward.
We indeed have a sort of internal database with standards, but it may require some effort to convince people to share this with the world and so on.
No, that's part of the problem, right? And so it's all over the place. This data, as far as I'm concerned, isn't the most useful by any stretch of the imagination because it's hard to get it into a analyzable format, for lack of better words. It's all native format for different beamlines at SSRL, Chess, and NSLS, and there's no really good database anywhere, but I really think there needs to be one. And I, frankly, given NSF in the US funding requirements of all data to be open after a few number of years, I don't see why there's not a good reason to have a large scale database. The only question is where would it be hosted, in my opinion. And frankly, given the way the internet works, I don't care where it's hosted. I just wish somebody would step forward and host it. And so I'm happy to throw it up here if people want to send it to me. But again, this is all operated kind of out of the goodness of IIT's heart, for lack of better words. And so I really think one of the synchrotrons should step forward and host a site like this.
Yeah, sounds like a good idea. Good. So I think people will try to follow this tutorial. I believe it will take some time to start working, understand. If something is not clear, what would be the best way to communicate, to ask questions?
So you can always email me, terryj@iit.edu, or you can always use the GitHub facilities for feature requests and things like that. So either one of those we'll be monitoring. So email to me or posting on GitHub will get a response.
Mm-hmm. And is there some kind of paper that could be?
So we have submitted a paper. It's under review right now, and we'll see what happens with it. But we basically put a rough citation that people could put up. But right now, the current paper is under review, and we're making modifications to it.
Mm-hmm. I see. Well, okay. So if there's there's actually a question just showed up. So the question is if the fitting would also work at edges other than K, like L2 or M45.
So the uranium was the L3. That was the uranium L3. So it works anywhere. And actually, I think this was the praseodymium L3 too, if I I'm correct. You just have
That's
to
right.
make sure when you're running FEF. Oh, that's not FEF, that's large. You just have to make sure that when you're running FEF, you select the right edge for your files.
Could you please share the screen? Yeah.
Oh, sorry, I'm not sharing my screen. Hang on one second. Okay, share screen. Share. Where is the share screen button? Okay, got it. All right, can everybody see that? So you just have to make sure when you're creating your FEF input file that you select the L3 or the M4, M5, whatever edge you're looking at when you create the FEF pass. So that's all that matters. So it works with any edge as long as the FEF input files are for that edge. And so right now we're working on a simple way to merge FEF files from different species if you have a mixture of atoms. Right now we typically do that by hand, but we're working on so you can pull FEF files from different directories. But right now what we do is we basically rename some of the FEF files. There are a couple ways you could do it. The easiest way is to, when you get these FEF files, let me show you a directory. So we get like fef0001.dat. So if you have a mixture, the easiest way to do this is to change one of these to a 1 and make them fef1001.dat and then put 1001 in the list. Or you can rename them sequentially. So you just have to put all the FEF files that you're going to use right now in a single directory. And I have an example of where I did that for Pyro. So here I've just put 20 paths sequentially. The first 6 are from a fluorite structure. The last 14 are from the pyrochlore structure. And because we're fitting in case space, we're still, even with this number of paths and all the fitting parameters, we're still way below the Nyquist limit, given the quality of the data. So as long as you keep the Nyquist limit in mind, you can have a fairly large number of paths. It takes longer. The more paths you have, the longer it's going to take to run. But like I said, if you have access to a cluster, you can fire them out, go home. Even if you're running them on a laptop, you can run them all fairly easily. And again, it should be fairly easy to write a script that starts them all on all the different processors.
Yanis mentioned earlier that it's very important to start with a good guess in the beginning when you start optimizing. So what would happen if the structure that we're trying to fit is it differs from the final output? If
it differs, you're going to get something like this. Well, let me go back one. So, for example, here is our fit with UO2 to something that was effectively a mixture of uranium carbide and uranium silicide. It's not going to fit. And so as soon as you see something like this, you know it's not a good fit. You know that's not the structure you have. So it won't be able to refine this into matching the data. That was one of the big concerns we had with the start was, would it be able to optimize these effective sign functions into anything? And the way we limit it, that doesn't happen. And so that is a feature in our opinion. And you'll get path values that are unphysical. So we have 0.14 here for the first uranium oxide path, and then we have a huge number of uranium oxygen multiple scattering paths. So this immediately tells you that this is not a good fit, and then there are no uranium path distances. So you can try if you have a bad structure. And so what we do when we're fitting data like this, we'll make up 20 different structures, 20 different FEF input files, we'll create 20 different paths, and then we'll run all of these simultaneously. And then we'll look and see which ones lead to reasonable physical fits. Then we typically make mixtures when we know we have a mixture of a compound. So we'll take a couple of the best fit structures and put them together, especially if we don't know what we have in advance. When you're irradiating things inside of a nuclear reactor, all kinds of bad things happen. It's a high radiation environment. You got neutrons flying around. You get neutron damage. Usually you end up with a mixture of things. And so we often have to deal with mixtures like this. And so that's one of the reasons why we do this. So people always like to see, can you rule something out? And so mixtures of UO2 and uranium carbide, UO2 and uranium silicide don't fit the data. So yeah, you will need the right structure or a structure that's close to eventually refine on what you really have in your material, and so that is important. But if something is not correct and is not in your data, you can't refine it to match your data.
Mm-hmm. I see. Yeah, there's one more question. It's about the how to decide on the number of paths that you select versus the number of independent parameters.
Well, that's so the number of independent parameters depends on how much data you have. So it depends on the data over the fitting range. So this is typically measured in about 0.05 inverse angstroms per K-space. So we typically take 1 point every 0.05 inverse angstroms. So if you go from, that's about 20 points per 1 unit in K-space. So if you have 8 units, 8 times 20, that's 160 independent points. So that gives you a lot of parameters to play with.
So that's
now, in point of fact, we usually keep it below half that.
Yeah, that makes sense. Matt specifically stopped on that during his talk. Yeah, there's a simple formula that allows you to estimate how much you can, how many independent parameters you can.
Yeah, well, the thing is, a lot of people fit in R space, and that formula isn't as straightforward in R space. So because we're fitting in K space, the data is the data. Now that's not 100% correct if your points aren't independent. And so if you're doing quick scanning, you can't use all those points because they're not effectively independent points. But if you're doing step scan or once you've processed it into K space, that's a pretty good rule of thumb that you're going to end up with 0.05. Some people use 0.075. In any case, it's still going to be a significant. And so the numbers for K-space fitting are worked out by Corwin Booth. And so there's a reference to that in our paper whenever it comes out. So so that's important to understand. You have to have a reasonable range, but given there are roughly 3 parameters per path, how we're doing this right now, you can have a lot of paths before you get close to 80, 90 parameters. Well, and so you basically in the optimization, when you have here, where's the path optimize? So we would take away the input paths. We would start with extra paths. So we would look at all the paths that are wrong window. We would look at all the paths they're in the R space range, and pick what range is important, and then we would try and include paths up to however far out we want to go, and then put those in, trying to include as many paths as possible without going over the Nyquist limits, and then optimize based on those, and it will throw out the paths that are not contributing effectively. And so what we do is we typically run this 100 times, again, because it's deterministic randomness. So you'll find that sometimes path 13 goes out and path 12 goes out in a different run. But when you do it 100 times, you'll see 13's in there 75% of the time, and 12 is in there 25% of the time. And so we build up a histogram that we use for cutting over multiple runs. So that's typically how we do it. Again, I wouldn't rely on a single calculation for deciding what paths to cut and throw out, but over an ensemble, you get a good picture. But that's how we do it. We run the path optimizer. After that, then you have a path list, and then we rerun everything 100 times for that specific path list typically.
Mm-hmm. I see. Good, thank you. So we're right on time. It's 1, and it's the end of our workshop. Thank you all for being with us all this 2 weeks, a little more. Thanks for your patience. Thanks for participation. Thanks to all the speakers who found 5 hours of their time to dedicate to this workshop. Thanks for presenting this new ways to analyze the EXAFS data. I'm absolutely sure that it's extremely useful for many people. I can't say yet if we are planning to repeat this workshop again, because we are impressed by the interest. We didn't expect so many participants to join this workshop. So there's a chance that we'll repeat it sometime in future, and obviously we'll inform all of you. So the recordings from the sessions will be available later, especially from this one. I think I'll send out an email with the link probably tomorrow. Then we'll compile a site that will contain all information, all presentations and examples that showed up during the sessions. In fact, it already exists. It's on the Confluence page. I will send the link again in the information email, and then concluding email after this workshop is over. And we would like you all to spend a couple minutes and leave a feedback regarding this workshop. It will be interesting to see what you liked and what you didn't like, and what you would be glad to see in future. And thanks again, everyone. Have a nice day, and maybe see you again in future. Bye.